Lorentz transform, and he's like, here, this will make it simple. He said like, we'll make it simple, and he gave us it's just a general response to the Sagnac effect, and it's just Lorentz transform at the end of the day, and it was so like it was like creepy, honestly. Like I still have like weird feeling about it because it was just like we're trying to investigate truth, and this dude is just like openly showing us his like dogmatic
Yes.
his dogmatic convictions or whatever.
Yeah, that's strange because from what I'm hearing from like Alan and stuff, like he's one of the more like sensible globe earthers. So I thought this was gonna be, especially with him like contributing to, designing at least his version of how the ether vortex works. I thought that this would be like easily digestible. So this is strange that I'm hearing this side from you guys.
I got
Dude,
this. I'll drop this comment he left.
yeah, let's see. What did he say here? He said, in the paper you link, the Sagnac effect is explained using a Lorentz transformation. This cannot be meaningfully substantiated and is unfalsifiable. It's pseudoscience. It, and then it can
That was
science
me.
that.
Yeah.
Yeah, then I can science that says Lorentz transforms are a standard part of mainstream science. Like this is the most normie NPC thing you could ever say. Like this is like everyone else does it, so why can't I? It's like it's still not false. Like this doesn't remove the unfalsifiability of the transformation, right? This
Right.
doesn't like this doesn't not make it pseudo science. Like
Did you use the word fundamental in there at all?
dude, Toby, you should have been like. So let me ask you this: is the Lorentz transformation a fundamental part of physics?
That's
Are
really
you a
dude, seriously.
he's a Lorentz
Seems like it.
fundamentalist, dude. So we should come up with like rhetoric for that, like a Lorentz fundamentalist or something. So they predate SR. So what he's talking about is Lorentz's work with an electron predating Einstein's special relativity paper in 1905. I think Lorentz's stuff was in the late 1800s. But anyway, he basically was trying to explain the speed of an electron variance by saying that there was link contraction. So he was the first to propose the mechanism of link contraction due to ether. And so when Einstein came through with that same framework and said, no, we can still contract, but just we don't need the ether. Like that's where that whole entire framework comes from. Just because it predates it doesn't add any validity to it at all. It's still a kinematic framework. It doesn't make it less kinematic. Okay. So he says, I'm not sure why you think it's unfalsifiable. Well, because the coordinate system transforms into in our reference frame, it's contracted. So we can't determine the variance of C. But when you invoke a frame that we can't go to, like the center of the sun, for example, or the barycenter of the solar system, and then you say, okay, from there, if we were observing it, you could see that the speed of light was the same. Well, that's not something that's falsifiable. That's a mathematic framework that only exists on paper. So
Was that I Can Science that said that during the show that you guys did with the ether, that he said, oh, the transformation was invented before any of this stuff. Was that episode or that show?
I think he did say that during that. I think we did touch on that, but
I
yeah,
feel like I feel like I did hear somebody, and it sounds. I'm trying to remember like where I heard it from. It sounded like that's where I got it from. But yeah, that's crazy rhetoric to think
yeah,
like just because
no,
something.
yeah, he tried. Okay, yeah. I explained it on that show because he tried to bring it up to undermine the usefulness of it or whatever, like us claiming it's invalid by saying or by us claiming it's invalid as a relativistic effect. He's saying no, it existed before relativity. It's like
Yeah,
it's like no, he was gonna like use that as his uh lead way to its validity, but it's like no, I already know the whole story, bro. Like it doesn't make it any less valid. It's still
right.
just kinematic dog shit. So yeah, I had to swoop in and take the air out of the sails on that. You're absolutely right. I do remember doing that now because I was like, damn, I feel like I just talked about
When you
this.
mentioned that, yeah, that's what I said. When you mentioned, I'm like, wait a minute, I feel like I just heard this from somebody. Like,
Yep, yep, yep. So there may be a discussion. There may be a discussion to be had there. Meanwhile, yeah, maybe right. Me, like if somebody were to, I don't know, make technology that didn't depend on a transformation equation to explain it, I don't know. Anyway, that
that'd
measures
been
the
nice, right?
Yeah. So meanwhile, the paper does a better job of explaining what Wang's setup is doing, in my opinion. So I think at this point, he's attributing your explanation as a misunderstanding of the setup or something, and he's saying like if you just look at that geometric expression of the transformation, it might help explain it better. I think that's what he. But that doesn't really answer what you said, right? This is just sentences. So that's why I included it. But it's like cool for including that because it was helpful. With the
Yeah,
diagrams and whatnot.
now I get why none of his shit was making any sense to me because it's like, oh, I'm not stepping out of the lab frame with you.
Yeah, it says you do not need the Lorentz transformation to explain or understand the effect that Wang showed. They are only included for the other paper for completeness. Well, they're included because absent of the relativistic one second absent a relativistic answer to chime in, like nobody cares because you can derive it without relativity. It was if the logic here is that the equation predates the relativistic solution, then the classical mechanics solution predates the relativistic one, so we win, right? Like that's stupid.
Oh yeah, and by the way, I didn't say anything about special relativity there. I just said the Lorentz transform. He's the one that said like it predates special relativity. Like, okay, who cares? Like
Well, he's
we're
so
talking about a specific experiment and a specific like effect, and I'm telling you that the Lorentz transform you're using to explain it is utter nonsense.
so the reason he's relating the two is because of the Lorentz transformation is special relativity, and he's saying his
Oh,
his
because it predates it, it's more valid or something.
well, no, not that, but the way that he's applying the contraction, he's saying that the mechanism of contraction is valid whether you accept special relativity or not, because he knows that we don't accept relativity. So he's trying to offer like an olive branch to say, well, contraction predates special relativity, so like it's not really anything, but like that's kind of what that was. And that's why he's mentioning it, because it's the only mechanism provided by special relativity, and he knows I do not fuck with that shit. He knows I do not fuck with contraction or time dilation, and it bothers him. So he's always trying to like explain it, or like give validity to it.
Xavier, what's up, man?
What up, Xavier? Wait,
You,
where's
you,
it?
you,
It's
you.
Drew here
What
tonight.
up,
There
folks?
it is. Yeah. Yeah, dude, I put the bat signal out and level heads, dude, so we could assemble.
Oh,
So we could
nice,
assemble the
nice.
lads. Hell yeah. So we got let's see, where were we at? Yeah, so that's why he's talking about that, because they're directly like this is his religion and you're questioning it. You see what I'm saying?
Yeah, no,
Yeah.
exactly. That's why it's like I don't even think I'm gonna bother responding because it's just like all right.
And it's tedious, right? At a point,
Well, that's why I made sure that the 2 comments I left were just too concise. They were just like concise sentences making my points, and it's just like I'm not even like.
Yeah.
And every time he just like he monologues with just like crapping out. It's like for an engineer, he sure likes to include a bunch of irrelevant information in his responses.
Yeah. So you do not need the Lorentz transformation to explain or understand the effect that Wang showed. They're only included for completeness. Okay, and then in short, I wouldn't let the Lorentz equations bother you. Just using classical equations, you'll find the same thing. Well, in the classical equations, our interpretation is that the speed of light varies.
Yeah, buddy.
And your
paper, like Wang paper, is classical. You nuthead. Like,
yeah, it's like in the way that Wang's talking about it, with preferred frames and a time interval change, dude. Like without, like he's literally talking about the speed of light changing, but without it putting it in plain English. So,
yep.
All right. So that's so that was the catch up on that. Where are we at now? So we're about to look at some papers, right?
Yeah, and then while you're pulling it up, everyone that's here tomorrow night at 7, we're gonna have Lucas here. He's a nuclear engineer, and wrote a book about thermal nuclear rocket propulsion. So we're gonna talk to him. He's also a fantasy author, so he may. It's funny. He's like kind of intrigued about flat Earth, but he claims it's just for like his fantasy novel's sake. But
Dude, we can
him
show
and
him
I had-
Nurth or Nern or whatever it is.
What's that?
Oh, when I had ChatGPT explain how you could make a globe map based off of Polaris correction angles in a fantasy land called Nern, that's a planar disk that wants to live on a globe. And ChatGPT
awesome.
totally
I
explained
never saw that.
exactly how to do it, and it was like under the guise of helping a civilization of people that live in a fantasy realm known as Nern, and
Nice.
and they all voted and said that they wanted to use navigation on a globe, but they were sad because they don't live on a globe. So we needed an AI to help figure out how to derive a globular coordinate system from a planar coordinate system, and it literally broke it down 1-to-1 exactly how FED breaks it down.
That's awesome.
So it's like, oh, okay. So I don't know, you know.
Well, I mean, just go buy a 360 cam, dude. Like, to me, that's like that illustrates so much about it, because a 360 cam just does. I don't know. It just shows how you can use 3D vision to produce a globe.
Yeah. Some sort of there must be some sort of hyperbolic relationship there, Toby.
Hmm.
All right. So let's see. The first paper we're going to look at is, where's my boy Marmot? So Paul Marmot. In 2000, the GPS and the constant velocity of light. So in this paper, he makes quite a few claims, and this guy was academically persecuted. Shout out to my boy Eric E, who just pulled up, who linked me this the other day. Really heartbreaking, man. You know how everyone's like, go get your award-winning go get your Nobel Prize for disproving Einstein. All right, well, let's see. Reaction to Paul Marmot's publications. Marmot's dissent about theoretical physics triggered a draconian reaction from the Canadian government, which immediately canceled all of his research grants, although they were not in the theoretical but experimental physics. The attack was followed by a reaction from the Lalo University administration, which forced Marmot to retire and even evicted him from his office. And there's a citation provided, so we can check that out at a later date, and we definitely will.
Wow.
So your boy spilled the beans. What did he spill? What was his crime? So the GPS and the constant velocity of light. Abstract. The Lorentz transformation and special relativity are unable to provide a relativistic physical explanation of the behavior of matter and light. We will show that these phenomena can be explained.
Realistic.
What's that?
That's a really important distinction there. Realistic physical.
Oh,
explanation.
realistic. My bad. I thought you said relativistic. Provide a realistic physical explanation of the behavior of light. We will show that these phenomena can be explained using Newton's physics and mass energy conservation without space contraction or time dilation. So, we're going to explain optical light phenomenon without the mechanism of relativistic effects.
Why would we do that?
So, and remember, this paper was said to not show that the speed of light varies and it's in line with relativity. All right, well, let's see if that's the case, because right now it's not looking so good. We have seen previously that the principles of the mass energy conversion requires that clocks run at a slower rate in a moving frame, and physical bodies become longer because of the increase of the Bohr radius. These results allow us to answer the question with respect to what does light travel. Oh, dude, Toby, we're going to get an answer to the age-old question. So, for example, when we move away,
what?
yeah, when we move away at a velocity v from a source emitting light at velocity c, with relative motion of the radiation as observed from the Doppler shift, we can explain logically that these photons appear to reach us at a velocity of c and not c minus v? Or how can we logically explain these photons appear at us at a velocity of c and not c minus v? That's a great question. And quick reference, real quick, we'll go to the ICD documents. This is, I think this one's 1996. Yeah, this is the first one. So what there's talking about here in GPS, or for example, right, a Doppler frequency shift in the speed of light. So Wang interprets this as a variance in the speed of light. I interpret this as a variance in the speed of light. Sagnac interprets this as like, so the classical interpretation of this effect is in tandem with the variance in the speed of light, this proportional Doppler shift velocity ratio that you can get out of this. So, and because GPS works off of a time interval system, the distance derived is going to be based off of the time in which their propagation was. So if there's a variance in that propagation, it's going to be proportional to the velocity. Otherwise, how is it going to purport? Or otherwise, how is the signal going to proportion a Doppler shift frequency that's proportional to the velocity, right? If it's not all changing proportionally. So without saying that C is changing here, right? They're just saying the Doppler shift of the frequency of the receiver carrier signal is proportional to the relative velocity of the receiver with respect to the satellite along the line of sight from the receiver to the satellite. So within that range measurement equation, again, the distance derived is accurate down to the millimeter, and that's based off of a variance in C, and that's why they measure that in the ECI reference frame, which is a frame that they say is rotating with the stars. So technically a stationary frame. You could kind of kinematically look at it that way, but it's rotating with the stars. So they say that that C is the same in this frame. And then when they transform to the ECEF frame, they have a remainder left over. So that's their velocity correction that they get, because they transform into a frame where they're actually assuming C, and then they're coming out of a frame where they actually measured the value of C.
Whoa.
And that the variance in that gives them their velocity correction. And the way that they word it is that it's just a Doppler, that it's just a frequency shift within a constant velocity of C. But obviously that's not the case, because if that were true, then the distances of GPS wouldn't work because of the corrections that they make after the transformation for the quote unquote Sagnac effect. Like the whole thing, the post transformation corrections completely invalidate special relativity. Because of this, it's literally the technology works off of the variance of C, hands down.
So,
Okay. What's up, Toby? Hello?
Is anybody else not here in Kotobi?
Yeah, I just wanted to make sure I didn't DC.
Yeah, I thought I lost you guys.
Let's see. I give him a second here.
A quick question, Alan.
What's up?
Isn't frequency inversely proportional to wavelength, like faster frequency, shorter wavelength type of deal?
Yeah, so when there's a shortening of the wavelength, it's inversely proportional to the frequency, and then vice versa. I have it. Hang on one second. I have the exact thing written down so we can get it exact.
yo, I messed up the cable that my mic's plugged into.
Oh, no worries, bro. Let me see. Where would that be? It was inversely proportional. Okay, it would be Zeeman effect. Okay, I think I explained it here, maybe. Nope. There's was it this one?
No, I'm just thinking, just with the Doppler effect, isn't that already a hint that there's going to be a variance with C?
I mean, dude, you would think, but they say no. So because they just say that the speed is the same, but there's a frequency shift and wavelength change within it that's proportional, that is like an energy change, essentially, but it maintains the speed. So
All right, cool.
so they're just like this. They're just like there's a never ending internal mechanism to change proportional, but maintain the same speed and never vary, or lose the energy to maintain the speed. Like whatever, dude. I just work here, bro.
Yeah, I feel you, bro.
But no, that's a great question, man. That's a great question.
Just
It's fucking great. It's like when C has to be C, bro, you got to make it work. You know what I'm saying? Like,
I know nothing
So-
about
I feel you, bro.
GPS, but that makes no sense to me. Like what you said, I just thought that was how GPS worked. Like, I never thought that they claimed it to be different than what you're saying. That's so crazy.
well, how did you think it worked?
Well, it's based on how fast you're going, right?
Oh yeah, well yeah. So it's like how would they derive that though, right? Without multiple ways to check the to get that right. So it's like it just so it turns out that there's a frequency shift that's proportional to uh to your uh to your velocity, and also that distance derived is accurate down to the millimeter based on that instance of when she received it. So that would also mean that the speed of light changed as well, because if it didn't, then that distance would be off.
Yeah, but yeah,
It's like a Doppler.
Right. So that's why they need to do a transformation from a different like from the ECI to like cover it up, because when they come out of this calculation, they need to explain how they like know your velocity and distance.
yeah, I get it. Yeah, that doesn't make sense. Yeah.
And they could only do that through just saying, "Oh, look, there it is."
They got
After
different. Yeah.
yeah, but they already got it in that first measurement. Like every because they say it's like three trilaterations or whatever they call it. So it's like, but each measurement is like boom, like they got it. Like it's just the triangulation is just for the location. They already have the distance and velocity in those measurements.
Okay,
Down-
so are they sending that into? So this is to get locations, right? Specifically,
Yeah.
that's the end goal here.
Yeah, this is when you get the signal received on your receiver, because the information of when it was sent, like that precise measurement of the time sent, is encoded with the satellite. This quote unquote satellite with the atomic clock information. That's how it's, because it doesn't have to, because the receiver doesn't have an atomic clock and all that shit. So it does it off of the accuracy of where it started.
So like from my phone.
No, like where the signal was sent, like from wherever, like from the
But if my
satellite.
phone's going to get my location, is that how that works? Does it use a frequency shift like that?
Yeah, inherently.
So like my phone, every time I use all these times, all these globers, literally every single, like I keep going like conceptually back to the satellites themselves, but like literally every time that my phone itself checks GPS, there's math right there in that exact moment that is ignoring the change in the velocity of light. Right? Like inherently, wouldn't it have to be like that?
So it would be. Let's see. They would probably send you some coordinate corrected shit to match out on the other end of it, though, because your device isn't going to be capable of like doing a bunch of transformations.
No,
So-
I know that, but like when they're finding my location, isn't that how that works?
Yeah, on their end.
Oh, but yeah, on their end, but
Yeah.
so that's dependent on the signal they receive from me? No, that doesn't make sense.
No, it's dependent on the signal that's sent from them to you. When
Oh,
it's
and then
when it's
that's using the GCS. That's because they already have their presupposed GCS at that point, right?
yeah, and then you're sending it back and going, "Hey, I got it at this time," and then it's going, based on that, blah blah blah. That's where you're at.
Oh, thank you. Okay. So got it. Okay.
All right. Eric just linked me this thing where this article is where Paul was asked to leave his office, man.
Oh, crazy.
Yeah. So from 1990 to 1999, Paul was an assistant professor from Ottawa. He was a researcher for the Hertzberg Institute of Astrophysics, the National Research Council of Canada Canada A in Ottawa. From 1983 to 1990, he was the director of the Laboratory of the Atomic and Nuclear Physics at Laval University in Quebec City. As the past president of the blah 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 blah, he was elected to the Royal Society of. Dude, he was a made man. You were a made man, Tony, or whatever. He was a made man. They brought him in, and he told the secrets. So, the Order of Canada was the highest decoration bestowed upon him from the Canadian government. Author, electron beam device, Paul Parma. Who's who? There was that. Let's see. All right, so not to detract too far into this, but let's see. So Eric, just to confirm, his thing was related to like the GPS spilling the beans, right? Because I heard it was over this paper, but I never looked into like the full story of it. If you can confirm. Actually, I'm going to save this.
Except I should unmute myself before saying anything. I just wanted to say I haven't read Paul Marmot's paper yet, so I have to look at it.
Okay.
Yeah, and it's right. You're almost at the paragraph where it says that he was asked to leave his office. It's right. It's at the end of that section, the paragraph before.
Right here?
About a little bit, about 3 paragraphs down. It's the paragraph before the section, the subsection.
Oh, right here?
Yeah.
Okay.
Well, yeah.
All right. Between 1978 and 1998, the author published several papers related to fundamental physics. Several of these papers are presented on the website here. We're definitely going to get that. In 1997 to 1999, physicist of the I should just keep it the same. Hold on. Physicists of the established showed a fierce disagreement with the fact that Marmot's research implied that the fundamental principle of physics were being questioned, although the experimental work, which could determine the energy of numerous quantum states, was highly appreciated and even honored in physics. The establishment required that the author stop questioning the fundamental principles of wow.
Go figure.
Wow, dude. The author was
He
informed.
questioned the fund.
Dude, he fundied out, man. Oh, wow. The author was
Called
informed.
them on their fundamentalism.
Sure did. He was like, hey, guys, why doesn't this work right? And they were like, shut up, Paul. Let's see.
Oh, wait. Fundamental. Is that the same as fundamentalism in religion? I don't know.
Dude, the author was informed by NERSERC, by a bunch of nerds, to stop doing the fundamental research, despite that fact being theoretical. It could require no research funds, and all the grants were used for experimental work needed for the electron impacts apparatus. Yeah, dude, it's always the fucking dude. If you're about to do something to fuck around with the electron, bro, you are fucked. J.J. Thomson put in a lot of work bolstering the atomic model with this, dude. Like, do not mess it up. This, wow, he was about to unravel the whole thing, and they, man,
They must have paid that JJ dude a whole lot of money.
and then all his, oh, dude, he was in the Royal Society too. He was a made man. So since the fundamental research was still going on the following year, the grants were cut to zero. Wow, dude, they just straight cut him down with his monoenergetic electron beam. Nice. Yeah, we'll have to look at the implications of this because this must be fucking devastating. This,
Yeah,
mu-
we know that's where to look.
yeah, they're not supposed to have this, so we'll be.
No, it almost seems like those people don't even know that they're made men. Until
Oh,
it's too late.
I think they know. I think they do mad gay shit with each other.
Yeah,
They're
but
like,
I think they don't. I think that they don't realize that the stuff they're doing is complete bullshit. And then when they do realize it and they go, oh, wait, like, I
oh
think we
yeah,
made a mistake. And then everybody turns around and go, no, we didn't make a mistake. Like, like
yeah.
one of those. And then it's too fucking late because you did all the shit, like,
Yeah,
and now
yeah,
they pretty much got you by the balls, literally.
dude. That's what happened to Paul. He was like, "No worries, boys. I got this. I'm gonna make a mono-energetic electron beam." He
And they said, no, you're not.
said, "No, the fuck you're not." In 1999, the head of the physics department came to Paul Marmot and said some shit in this language right here that we're gonna translate here. So, translate. He said to him. He said, "It's not your office we want. Your problem is that you question the." Whoa!
Whoa.
What the hell, man? Oh, let's see.
Somebody come up with a meme for this, please.
Let me make sure I'm reading this correctly. It's not your office we want. So it's not that his office they needed to relocate him. There was like some environmental issues, some allergies or something, and they had to move him. He said the problem is that you question the fundamental principles of physics. What?
Well, I think it's even more
Yo,
like
that's straight gangster shit right there. That's Jersey shit. That's what that sounds like right there. That sounds like where I come from. That's what they do to people when they open their mouth.
So let's see. Causality
the causality
principle.
principle.
Okay. The future state depends only on the present state. Okay.
Covariance.
It makes sense. Let's see. What was the oh wait, is there a first principle here? It says, okay, this can also be locality principle. Okay. So causality, covariance principle. The physics should be invariant under arbitrary coordinate transformation. Oh, no way. So he definitely wasn't doing anything to violate causality, right? Because that would be like grandfather
Yeah.
paradox, like insane shit. So we can rule this out. We can rule out this. So we're left with
He did 3 and 4, it seems like.
we're left with covariance principle. The physics should be invariant under transformation under arbitrary coordinate system. So, for those who aren't familiar, Einstein's special theory of relativity, the first postulate is that all inertial reference frames are equally valid. This is a pledge of allegiance to what's called Lorentz symmetry or covariance. And this says that under these mathematic transformations, under the Lorentz transformation with the gamma factor correction to time and space, that all the laws of physics that they transform will be invariant, so like they won't change, so they're not going to be messing around or whatever. So that this is how they would mathematically substantiate their claims, by doing a transformation and then validating that the laws of physics are not mathematically being changed. And they have a lot of freedom with this, though, through they can literally change the coordinate system to contract, and time can change. So they have a lot of leadway to get there. But this is a big thing that can't be questioned. So like a big thing that involves covariance is something like the speed of light being the same speed. That would be a fundamental law of physics. That would be a fundamental principle of physics, that the speed of light is the same in all frames, because the second postulate of special relativity is that the speed of light is constant for an inertial observer, regardless of the motion of the source. So if you were to start saying that the speed of light is different, like this would be questioning the fundamental principles of physics. So the invariant, and then number 4 here, we have invariance or symmetry principle. That is that space-time is homogeneous. And so what is that in regard to? That's like Is that for the isotropy of the calculations that they do, where they assume that the universe is at rest and all that? I'm not super familiar with that. I think that's in regards to that, and then the equal probability. Hold on. Let's see. Okay, so the invariance principle is in states that space is homogeneous. So equal probability principle. This states that all states in an isolated system are expected to be occupied by an equal probability. The 5 basic principles are considered in physics, are considered as physical common sense. All right, so these are the basic principles to start with. So he was questioning, you know, these. And you can't do that apparently. Apparently, if you do that, somebody will come to you and ask for your office and tell you that it's not their office they want. It's the fact that you're questioning this stuff. That's cool. So, go ahead and just disprove Einstein and get your Nobel Prize. Go ahead.
But don't forget, we got those videos and pictures of you.
Yeah, we got the videos, we got the pics. So, with the results of this, keep it real shut. So let's see. From the example of a Doppler shift, so we can explain logically that the photon appears to reach us out of light. How can we possibly say that the speed of light is the same with this frequency shift that we were talking about earlier, and not c minus v? The conventional explanation relies on special relativity, but it implies an esoteric space-time distortion, which is not compatible with logic. It's a bold claim, Mr. Marmot. Why would you say that? This paper gives a physical explanation to how the velocity of light is really c minus v with respect to the observer, even if the observer's tools always measure a velocity that represent the number c. So, what are we saying here, guys? This is like dark magic wizardry, right? So this guy got kicked out of his office for all this. But what did he just say? He's about to propose another theory as to how the speed of light can be the same, but we measure it not the same. And so what I'm thinking here is that they don't want there to even be another possibility where C can be the same without relativistic effects. Like, they got to monopolize it this hard. Because this isn't even that damning if he's going to turn around and then try and describe relativistic mechanisms. Because that was something that I Can Science That said, is that Paul Marmot ends up arguing for length contraction as a mechanism, but like through classical effects. But it's like, it's not the answer. But clearly the phenomenon is the takeaway here isn't that the speed of light is the same, right? These are proposing secondary explanations to explain why it's how it's the same, how it's really c, but we're measuring it not c. We will explain this problem is crucial in GPS global positioning system, and in the clock synchronization, the Lorentz transformations become quite useless. The apparent constant velocity with respect to a moving frame is the most fascinating illusion in science. So, well, I guess it's like basically, dude, yeah, he went too hard at Lorentz and relativity. He's calling it unnecessary. Let's see. All right, so let's see. We got the French derivation here for some reason. All right. Many experiments, like the Michelson-Morley and Sagnac experiments and others are testing the fundamental nature of light. It is conflicting to observe that the velocity of photons is measured as a constant. When the observer moves away from that light source, photons, just as any other particle, possess an independent existence and are not created by by physicists' thoughts as claimed in quantum mechanics. Dang, he went real hard. Since the other particles are measured with with additive velocity v plus v with respect to the moving frame, why can photons not obey the same rule? It's a really good question, Paul. I'm gonna do some
Bro went
highlighting.
after C and quantum. I'm surprised he's still alive, bro.
Dude. So let's see here. All right, so since Newton's mechanics had shown that all relative velocity produces a Doppler frequency shift, we might expect logically that some special phenomenon prevents us from detecting the real change of relative velocity. It is quite incorrect to believe that this phenomenon cannot be explained using reality in Newton physics. As required by the principle of mass energy conversion, Marmot 1997, the nucleus and electrons forming a local standard reference meter of a moving clock acquire some extra mass due to the materialization of kinetic energy. Okay. Does it? All right. So let's see here. Where are we at? Let's see. Quantum mechanics shows that this increase of energy changes the de Broglie electron wavelength. Consequently, the Bohr radius and clock rate. It is surprising to find new hypotheses like space-time distortion and even more suggestion of new logic to explain these observations, while it is not taken into account that the rate of the moving clock is naturally modified due to the increase of mass. Following the absorption of kinetic energy, the application of the principle of mass energy conversion explains naturally all these experiments. We must add there that there was only one real logic, an assumed superior logic capable or applicable to modern physics and not compatible with real logic. We must recall to an empirical equation used to predict the outcome of a physical system is not an explanation. No way. Huh. I could have sworn that if you had an equation to represent the bending and warping of space-time, that therefore meant in perpetuity that space and time are bending. When there is no physics underneath these mathematical equations, they give empirical predictions of what will happen to the system. Mathematical equations generally deal with time symbols but never explain why. A real explanation must answer the questions of causality, which is asked by why. The equation is never the cause of the phenomenon. Shout out to Marmat, dude. He gets it. Switching between frames. Let us consider the frame of reference of a small star cluster with stars having all having the same velocity as illustrated in figure 1. One of those stars is our sun, which is surrounded by the earth moving around it. In that star frame, an observer measures that photons are emitted with the velocity of c with respect to the star system. That light, hv on figure 1, travels towards Earth, but as Earth moves away from it with velocity v subscript e, with respect to the star system as illustrated in figure 1. So we got light waves going towards the Earth. We have the Earth moving away from the photons that are being emitted in the star frame. So motion of the Earth in an absolute frame. Earth motion in an absolute frame. So photons are some sort of electromagnetic wave packet with which travel at a velocity c with respect to the star cluster. Consequently, those photons must logically travel at a velocity c minus v with respect to the Earth as it moves at velocity v. As demonstrated previously, the strict application of the principle of mass energy conversion leads to the slowing down of the clocks and the increase of the Bohr radius, which produces an increase of the length of matter. More far-reaching applications have been presented previously by Marmot in 1997, but in this present paper, we need to use solely the increase of the length of the matter and slowing down for slowing down the clocks. Using classical physics with these two natural consequences of mass energy conversion is totally sufficient to explain all the problems related to special relativity. The Lorentz equation becomes useless. Previous readings of the book Marmot, 1997, would be extremely helpful, even if the main explanation and relationship are briefly recalled here. Let us simplify Figure 1. On the right-hand side of is Figure 2. The Earth is moving at velocity v is now substituted with a train moving at velocity v with respect to a stationary frame S. An image of the moving train appears on the upper left of Figure 2. At the previous time, the physical length of the moving train is established here as LV, or L subscript V, which is the distance between clocks A, or alpha, and beta. Below, we see the train at rest at the station S before it started to move. Light emitted from the star system is now represented by a light emitted at location A on the station of frame S. In Figure 2, the length of the station and the distance between LV and the clocks A and B. In Figure 2, the length of the station is the distance L sub V between clocks A and B. The distance
is equal to the length of the train in motion. Of course, the length of the train L at rest is shorter before it started to move. As explained previously, Marmot 1997, the relative length L of the train in motion with respect to the train at rest, L subscript, what is that? I can't, it's tiny for me.
S.
Subscript S is L subscript V length over lengthen or over L subscript S equals length in motion over length at rest equals not sure.
Gamma.
The parameter gamma is equal to 1 divided by 1 minus velocity squared divided by speed of light squared to the half power.
Yep, that is the Lorentz contraction.
Oh, okay.
Yep. So that's when you see the gamma correction, that's the Lorentz contraction. Or this is the.
When I see V and C in there, it's kind of a giveaway too.
Yeah. Well, not necessarily. You just got to look for that gamma.
Gotcha.
So let's see.
So capital letters are used to describe physical lengths. The sub-index gives the location of the physical body. To be coherent, the physical length L subscript S and L subscript V must be compared with the same standard unit of length in the same frame. We have seen, Marmot 1997, that when we carry a standard unit of length from a rest frame to a moving frame, that standard length of reference also becomes gamma times longer. For example, the relationships between the lengths L subscript V and L subscript S in equation 1 can be verified experimentally if at one instant clocks alpha and beta on the moving train leave some marks on the station frame that can be measured with the station meter.
All right, and here's our diagram of a clock and the moving frame or whatever with the train. And this is the length of the train station. The stationary length and then the moving length. So, see clock synchronization in a moving frame. Okay.
However, since we deal with observers measuring lengths and recording clock displays using their proper units, we need to determine the number of local units in other frames. Of course, when the standard meter used to make measurements is moved to another frame, its physical length is also changed. Therefore, when the moving observer determines the length of a moving body, he is now doing it with respect to the local standard meter, which is different. The number lambda is that right, lambda?
I don't know
No,
what
that's not
this one
lambda.
is.
I don't know what I just
Something
saw an
else.
L, so I said lambda, but
Yeah.
I don't know what the
Yeah, I'm not sure.
the number L, we'll say, represents the number of times the designated standard units of length have been counted when measuring, well, actually L. The number of times a moving particular length is longer than the standard length located on the station S is represented by whatever that symbol is, subscript V,
Cursive L.
and then S.
Yeah,
What is that?
that was I think that was the station, I think, if I'm not mistaken.
Mm.
Yeah.
Okay.
So right here.
The quantity inside the square particles or the square parenthesis S or V indicates the information about which the standard unit is used, either at rest or moving.
Oh, so stationary, and then a V would be if it's moving. So cursive V would be the velocity in motion relative to stationary.
Oh, and then the sub indices give the location. Okay, that's good. That makes sense. Okay. Of the measured body. Okay. So the sub indices S or V in that symbol sub S, that symbol sub V, give the location or sometimes the frame of the measured body. We see that the same rod at different locations can be designated by 4 numbers. L subscript S L. Oh, geez. So what is this explaining here?
He's laying down coordinates for a coordinate system transformation. He's defining the parameters of what's being measured and transformed, and what each coordinate contains, like what the information contains in that coordinate.
Gotcha. Okay. We take the example when the observer on the train uses his local meter to measure the length of the moving train. He finds that this number, L or whatever that is, subscript V, square parenthesis V, is identical to the number of units on the station. Weird L symbol, subscript S, square parenthesis S, before the train started to move, even if it is not the same physical length, L subscript V more than L subscript S. Identical to the number of units on the station. Sorry, okay. However, when the same physical rod in the same frame, constant L subscript V, is measured using different standard units, V or S in square parentheses, the number measured with respect to each standard lengths unit, V or S, follows the relationship weird L subscript V square parenthesis S weird L subscript V parenthesis square parenthesis V equals gamma. Since the moving observer uses his local moving standard units, he might believe that the length does not increase when his own velocity increases. He does not realize that his train is physically longer, but this is not measurable because his local standard meter has increased in the same proportion. In doing local measurement calculations, he will normally use the number weird L subscript V square parenthesis V to calculate the length, which is identical to the number weird L subscript S square parenthesis S. In fact, equation 2 also implies that the real physical length L subscript V is equal to gamma times L subscript S degrees. I can't see what that is.
No, it's just a period.
Gotcha. Oh, okay. In order to apply physics correctly,
You got math. You got math brain.
Yeah.
Like, are they trying to multiply that?
In order to apply physics correctly, the moving observer must compensate for the fact that he does not possess the same standard unit of length as when he is located on the station frame. Wow. In order to apply physics correctly, the moving observer must compensate for the fact that he does not possess the same standard unit of length as when he is located on the station frame. Therefore, he must apply a correction due to the change of length of his measuring local standard meter as given in equation 2. So he's just kind of laying it all out how this relativistic covariance is supposed to work, right?
So he's
Or I guess
laying.
how it's
He's
observed.
yeah. He's gonna lay it out to explain, instead of through the length contraction time dilation. I'm guessing he's gonna set it up through a mass energy conversion, where the velocity is going to explain the apparent length and what's it called, time variance. Because Science that said that he was basically just replacing the mechanism. So like this is just his explanation of what's happening. So I'm just kind of waiting until we get to I don't know I'm trying to get to where we get to the equations at for the clock synchronization stuff.
Wait, before you get to that, a quick question. This is for both you and Toby. Let's say somebody had a question about the moving body. Let's just pick instead of just trying to fix for with the transformations. Let's just pick two arbitrary points. The space between two arbitrary locations. What would they say? What apologies have you heard to I guess give apologetics to how the space between 2 points can be simultaneously different for the moving body with the stationary body without uprooting what it means to be to what length means. What's the simple apologetics that they give?
So the simple apologetics is not ever being asked that question, and then the other apology, and then like not knowing the answer, and then the other is relative simultaneity. So they just say that the contraction is apparent and it's not real; it's relative to the observer or whatever. So that's what they say.
Gotcha.
But then obviously you get into the problem with GPS doesn't account for any sort of corrections based on observers' velocities relative to one another. Like it would, dude, it would be a never-ending cascade of corrections. Um, but they don't have to do that. So it's like dead giveaway that relative simultaneity, like conceptually as your jumping off point, it doesn't even manifest in reality when there's a when a GPS would be a perfect way to for like relativity to really shine, because they could have been like, oh, why doesn't GPS make sense? Why are all these events not in a cohesive timeline? It's like, oh, we have to account for relative simultaneity, but like that didn't happen at all. It's just everything worked on a cohesive timeline, like no problem. So there's literally no justification for accepting the transformations, contractions, and apparent of anything like that. But if you were like going to or whatever, your reasoning would your end all reasoning would be relative simultaneity apparent relative to the observer.
Got it.
All right. Yeah. Let's see where are we at.
You want me to keep going?
Oh, I'll do a little bit because I haven't even read this part of it stuff. I just like skipped through to like the like right around here. I think is where I started with the Einstein stuff. So I'm interested in hearing what Marmot had to say about it, because I didn't know he tried to replace it with his own thing, which is like equally, not valid. But I get why he tried, right? Because Mickelson
Yeah.
Snorley. So I get where he's coming from. It is very cool. So let's see here, because the effects are real, right? And then he's just like deriving math to explain it within the confines of a not relativistic manner. Because remember, the concept of mass energy equation or being equivalent predates relativity, right? So like this is like it was a classical interpretation, and
Interesting.
yeah, just expressed with different coefficients, because that's what they used to build the atomic model. They used J.J. Thomson's coefficient to define or to basically derive the mass of the electron, so that they could give it momentum and spin and all that stuff, and like make it a particle. And then they built everything relative to the mass of that and the charge of that. They just had to get a little mass out of it, a little mass out of that energy, bro. Just give me a little bit of that mass, bro. Give me a hit of that. All right, so we have seen that due to mass energy conversion, it is impossible to switch matter between frames without changing the physical length of the standard measuring meter. So yeah, this gets into the covariance issue that Einstein was experiencing, right, with the dynamics of the lab frame, or being dynamically covariant with the lab frame and rest mass. So, uh, for the same reason, it would be impossible to switch the standard clock to a new frame without altering the clock's frame rate. At the same time, matter passes from the station frame at the moving frame. We see that Marmot, 1987, that the atomic clocks change their rate because of fundamental particles, electrons, etc., of the atoms have acquired energy equivalent mass. So they're seeing a energy change fluctuation, and then they're attributing that to like the electron gained mass. And then because of that mass increase, it's now not behaving how it should be. But keep in mind, this is a kinematic description of the behavior. This isn't like, this doesn't have like this. It's obviously not dynamically what's happening, because they had to invent the strong and weak nuclear forces to supplement the whole particle theory. But um, this is just kind of like looking at it through the lens of how they're interpreting it, right? So of the atoms, we have acquired energy equivalent mass. We've seen that the rate of the moving clock alpha and beta on the moving frame is gamma times slower by the rate of the clock of A or B located on the rest frame. Consequently, there is one local second V in the measured on the moving train, and a moving observer must realize that in fact for that in fact a longer time interval has elapsed because the local moving clock is slow. During exactly the same time interval, the slower clock rate of the moving clock produces a smaller difference in the display, delta CD sub V, than the display observed at the rest clock, delta CD sub S. The relative difference between the clock displays between the reference frames is given by the relationship. They got their equation here. So delta CD sub V over delta CD sub S equals delta CD train over delta CD station equals 1 over gamma. The train observer, must take into account this calculation, that his clock is moving as slow, and that when he is measuring, just as when he is measuring lengths or whatever. So the time interval is changing, and also the distance is changing based on his velocity, right? So he knows that the two clocks, A and alpha, located on different frames, will show a difference in display apparent time, right? So we're getting into the like. So I don't feel like we can. God, fuck. Like I don't care. Like this isn't you know. So let's get to the Einstein stuff. Any objections to skipping over that, like the rest of his kinematic explanation to it?
No, we're
Yeah,
good.
I'm good with that.
All right, cool. Because like I get it. Like he's trying to replace it. It's all good.
I will say, like, it was interesting parts of it for
Yeah.
sure.
Yeah.
It kind of put a new light on E equals MC squared, honestly, for me.
Yeah.
But yeah, it's still just more kinematics, really.
Yep. All right. Einstein's clock synchronization technique. On the station frame, an observer calculates the velocity of light using the proper units, stationary s, and the standard method used by Einstein. A pulse of light is emitted from location A towards B, see figure 2. The station observer measures the velocity of light, calculating the quotient of the length L sub v divided by the difference of local time between the light emitted from A and received at B, see figure 2. Since the train is in motion, for the station observer in the distance L sub v between A and B is represented by cursive L sub S stationary S, and not cursive S stationary S, because the train is really longer when in motion. Measuring the time interval means that the station observer records the display shown respectively on both clocks at the instant light is at the location A. Whatever. CD sub A, and then the latter B, CD sub B. This experiment gives C. So we got cursive L sub V stationary S, CD sub B stationary S minus CD sub A stationary C equals C. We notice that the clocks A and B and alpha and beta have not been synchronized yet. Let us apply Einstein's synchronization method to the moving frame. A pulse of light is emitted from the location of light of the station. Later at the moment, some photons pass through the location at alpha, and the clock displays CD sub alpha velocity v. On the clock, alpha is recorded. Also, when the light reaches location beta, the display clock on beta reads CD sub beta velocity v, and is recorded. As seen by the train observer, the velocity of light on the moving train is given by the following quotient: the distance cursive v or cursive subscript or sub v velocity v between alpha and beta divided by the difference of the clock display between beta when the light arrives minus the clock display alpha when the light passes alpha. Before calculating correctly the velocity of light on the train, we must synchronize the clocks alpha and beta on the moving frame as suggested by Einstein. We synchronize the clocks alpha and beta inside the moving frame in the usual way. It is a two-way velocity clock synchronization. The Einstein synchronization technique is used by the moving observer, the moving observer is the following. A pulse of light is sent between the clocks alpha and beta. The difference of the clocks is delta CD sub A minus or sub alpha minus I don't know how to read that, but a bunch of the whole coordinate systems of all the clocks, right? and the clocks A, alpha, or beta is recorded during the return trip for the light and alpha and beta. In the second part of the experiment, at the moment of light from alpha is received from beta, the clock display on beta is set in the same frame or set to the same value as the initial clock displayed with alpha when the light is emitted, plus 1/2 the difference of the clock display. So 1/2 delta CD sub A or sub alpha B alpha velocity measured previously. The light making a two-way trip between alpha and beta. The local apparent time means what was displayed on the moving clock. One must recall that this measurement must be done using all local moving frame units velocity as displayed directly on alpha and beta. What the hell did we just read, boys?
Oh, I don't know, dude. You go back up to the last part.
Yeah.
Go down right here.
Okay. Right here?
Yeah, I'm reading. Hold on.
Okay.
Since these calculations are verified by the GPS and the Sagnac effect, we will neglect all higher power of V divided by VC. What is that? Velocity divided by the speed of light?
Yeah.
Since these calculations are verified by the GPS and the Sagnac effect, we will neglect all higher power of velocity divided by the speed of light because they modify the results by quantity is small. Okay. Further investigation involving a higher power will be considered later.
Oh yeah, that was from where we tapped out on his synchronization method. So I think he was see, the calculations and quantities implied have varying large quantity size. Okay. Since the calculations are verified by the GPS system and the Sagnac effect, we will neglect all the high power velocities. So I think he's saying like the justification for trying to explain the mechanisms of contraction and whatnot are valid because they exist. Is that kind of what he said?
I guess that's what it seems like. Just like he says they exist and has kinematics for all of it, basically.
I'm sorry, say that again.
He says that they exist, and then he gives kinematic examples showing that they all exist.
Yeah, and trying to explain them through his mass energy relationship. Yeah, that's what it seems like.
It's interesting.
So, all right. So then we were on the Einstein synchronization method. So, Einstein synchronization technique used by moving observer is the following: a pulse of light is sent between clocks alpha and beta. Where's the diagram at for this anyway? Wasn't there supposed to be a figure? Okay. Second. Let me look at this on the side. Come on. All right. Where were we at? Einstein clocks. Okay. So the difference in the clocks. Okay.
Like you say there for one more second. Sorry.
Yeah.
I don't get this.
So let's see. The difference of the clock display is for this coordinate system here. So this would be. I don't even see clock display. Okay. Okay. So clock display, then A, B, A. So whatever the clock reads, A to B, clocks A and B. These are on the train that's in motion of a distance L. Okay, inside, and that suggests we use this thing inside a moving frame. Okay, so these are supposed to be train cars, I guess, so to speak, right? And there's a clock, an atomic clock on either end.
Okay.
And then this is the stationary frame, two clocks, same location. And then it would be so the time difference between these two clocks after they complete a return trip, around their circuit. And then that time is synced to this guy, I guess, or the difference between that. Something is what they observe. Kind of what it's what I hope is right.
Difference of clock display.
Oops.
Okay.
And then they're saying that you apply the. Let's see. You set the same value. Okay. So the difference of the display clocks from the moving frame on the clock's alpha or beta, the moving frame, is recorded during a trip of light between A and B. So a trip of light. Jesus. Okay, so a trip of light between alpha and beta. The second part of the experiment, at the moment of light from alpha is received at beta. So it's the ticking between the two clocks.
So it's essentially doing like a same thing what you would do with GPS, but from the back to the front of the car, right?
That's what it
One's
sounds like.
stationary, one's not.
Dude, why does it seem so hard to understand it? That seems like what it is. Like it's just calibrating what the difference would be after it completes, or like how out of sync it would be after it completes a rotation, right?
The thing that's confusing me is scroll up again a little bit.
Mm-hmm.
The pulse of light.
Okay.
Pulse of light is sent between the two clocks,
Okay.
alpha and beta.
So clock alpha, clock beta.
But that's that car is going to move forward, right?
Yep.
All right.
Okay, and then the second part of the experiment, the moment that the light from alpha hits beta, the display clock on beta is set to the same value that was on this clock when it was emitted. So, okay, so this kind of makes sense. So, to this, it would be like, so it would be like this clock is encoding what time it's activating at or whatever, right? And then it's sending its signal to this clock, and then this clock doesn't even turn on or activate, until it gets this signal. And when it gets this signal, when it turns on, it activates with the time that was sent from this clock, so that they're both in sync while in motion, right? Because the synchronization for something that's in motion is going to be it would be different, right? Because your contraction is going to be different, right?
Yeah. So okay.
So they're saying to even get the. Oh, okay. It's making okay. So because all these relativistic effects supposedly exist, right? And it's all motions relative, blah blah blah. The only way you could sync a clock, right? Because you couldn't do it on Earth, and then per se use the Sagnac effect to have it correct for the relative velocity shift from electromagnetic retardation due to the ether, right? Like that's out the window, right?
Yeah.
How you sync a clock? You would do it while it's in motion and do this configuration here, where like basically a thought experiment to activate the clock, right? Or like how you would
it's a way to throw out the difference,
right?
Huh.
To start relative motion.
That's what all this is. Okay.
Oh, man.
Wow. Okay. That's so.
So this is the dude. I didn't even so like I've seen the math equation, the gamma correction basically for it, but I didn't understand that their methodology was that they had to do it from a clock in motion first. So they're already starting off with that.
They're using the actual measured difference in velocity to then turn around and take that away.
Okay, so
for their synchronization.
So in Einstein land, that would be how you validly do it, but because the relative velocity, changes it proportional to its velocity, it's essentially just, or what we're gonna find out here, because I've already read the other half of the paper. What we're gonna find out here is they just equate for the Sagnac effect. So this is conceptually how you would have to sync a clock if relativity were correct.
Gotcha.
So
Okay.
so he's laying down Einstein clock synchronization based on the theory of all motion being relative and how you would have to sync the clocks being in relative motion.
Got it.
All right.
I think.
No, that's it. That's if that's not it, then like we're fucking sleeping. Like that's it.
Yeah.
So let's see here. The difference of the clock display, blah, blah, okay, measured. All right, so we've figured out what this is. This is the clock synchronization method. Your clock's in motion. It sends a signal out encoding its information of when it started. Hits this because he says like conceptually like it just magically happens, but like we know GPS would like this is how it would work. You would hypothetically send the time. It sends this, and then this activates with that set time. Boom, they're both in sync now, despite their relative velocity differences, right? All right, so that's how Einstein says a clock sync works. So the GPS and the constant velocity of light. It is utterly important as explained in more detail, Marmot 1997. In the case of clocks A and B on the station, is the synchronization method is identical as above using clocks A and B at the station. So he's replacing the conceptualization of it with his thing. Cool. So using the clocks A and B at the station at the length, cursive L sub V stationary S. Finally, the synchronization must be done between clocks A and alpha. The most reliable way to synchronize them is that the same value display on clock alpha passes just beside clock A, just as the half figure goes by. Cool. So to sync the ground clock with the moving clock, as it's moving along, it sends its time to the stationary clock, and also when that clock gets its signal, it sends, or when the beta clock gets a signal from the alpha clock, it also sends a signal from the beta clock to the B clock and says, "Hey, I was activated from the alpha clock at this time." So this is to cohesively sync the moving unit with the stationary unit in Einstein relativity.
Got it.
Whew, fucking A. All right, finally. I guess we could have just read one more sentence down to put it all together. Because it made a lot more sense after reading that part. All right. Anyway, the most reliable way to synchronize them for this value to display blah, blah, okay. So it is important to add that it is also demonstrated another well-known procedure leads to a perfectly identical synchronization between two clocks. This is used by several authors. We refer to it in Marmot 97 as method number 2. Definitely going to look into that. It consists as carrying a third clock mu at an infinitely slow velocity on a moving frame between alpha and beta. This leads to a synchronization of alpha and beta with respect to alpha identical to Einstein's synchronization method explained above. Of course, this method is also applied successful between A and B. The reader must refer to chapter 9 in the book. So we'll hit that up later. Let's see. To see that the two models lead to an identical synchronization of the clock when used on either a rest frame or a moving frame. Okay, so to see that so that this other method he's proposing with a third clock, he's saying can substitute this synchronization method. All right. Let's see. All right, synchronization of moving clock. Okay, I'm not super interested in this equivalence of the third clock synchronization setup.
Yeah.
Okay, so
that's fine. If you're fine with it.
Yes. Okay. So we have seen that these clocks are given by equation B. Okay. All right. All right. Using Einstein's synchronization method, equation 13 gives the difference of the display. So this is the summary between the three methods given. So we have Einsteinian clock synchronization, the 3 clock method, and the or no, this was the Einstein one. Whatever Marmot was about to propose for number 2, and then we have that was the 3 clock method. So what was the other one?
Table of clock, is that what that said? Down below?
Right here?
No, never mind. Never mind.
All right. So anyway, using Einstein's synchronization method, equation 13 gives the difference between the displays at the same instance between the clocks alpha and beta. This difference is constant in time. The original Einstein's clock synchronization method was perceived as an attempt to set up an identical display on 2 remote clocks alpha and beta on the same frame at the same time. However, unexpectedly, in a moving frame, this synchronization method does not give the expected result as obtained on the stationary frame. Equation 13 shows that the display on clock beta gives an apparent time which is earlier than the display on the clock alpha. This is
What a surprise.
This is in fact coming out of the inevitability from the principle of mass energy conversion and the Einstein and Einstein's clock synchronization method. So, or there's a velocity shift proportional to the velocity of what's propagating inside of the clock that's used to determine time.
Yeah, this is coming out inevitably from the principle of inevitably. Just, but just when it's convenient, inevitably.
Inevitably. So yeah, we're gonna hit up equation 13. All right. So, because this is all gonna track back to our boy Sagnac. Do you want to read? You want to read a little bit? Take over.
Sure.
All right, cool.
This deficient synchronization of clock beta is responsible for the Sagnac effect and will be explained below. This difference in clock synchronization is normally undetectable. What the fuck is that? Like, what? How are you going to inverse that?
Well, normally it only affects electromagnetic propagation wavelengths when you're trying to determine a precise velocity or distance using the measuring stick known as C.
Dude, like, look at right above that. So it says he goes from one sentence saying it's inevitable, and then the next sentence saying it's saying that it's normally undetectable.
Yep. I mean, I think he's probably saying, like, in practical sense, like if you were an observer because this is like you got to have basically an interferometer and break the wavelengths down to the hundreds or thousandths to
Yeah.
So
yeah, it appears quite natural. Yeah, that's kind of like the whole thing of like, yeah, linear motion being detected with it is kind of a big secret in physics.
Yep.
From the above calculation, we also see that when clock, what is that one?
Mu,
thank you. That clock mu returns in the opposite direction from beta to alpha at its arrival. The clock display on mu is then again exactly the same as the clock display carried by the returning clock alpha. The phenomena is reversible. Consequently, equation 13 is identical to equation 9.37, Marmot 1997. Above calculation, I'll see that one.
All right, and then we'll go down here.
We have shown above that the synchronization of clocks on a moving frame is such that clocks alpha and beta must necessarily be synchronized with a different display at the same instant. This is required even if both clocks alpha and beta are located on the same frame. However, both clocks A and B at each extremity of the station frame show the same display at the same instant. An observer on the station frame could observe that clocks alpha and beta do not show an identical display at the same instant. However, the observer on the train could not detect any difference when synchronizing his local clocks because both methods of synchronization using light or carrying clock mu agree with the above Einstein's discordant synchronization between alpha and beta. Since this phenomena has not been discussed previously except in Marmot 1997, in order to give a non-ambiguous description, we present a table of clock displays appearing simultaneously on 4 clocks, A, B, alpha, and beta, as a function of the apparent time on clock A for each successive second, S, as given in equation 13.
All right.
Respective clock displays.
Okay. So respective clock displays.
Okay. Let us calculate the distance L sub 2, see figure 2, traveled by a beam of light emitted at velocity c from location A at rest on the station during the time light passes from alpha to beta located in the moving frame. Using Galilean coordinates, we calculate the velocity of the photons moving at velocity c minus v with respect to the moving train. The photons must travel across the moving distance, L subscript v square bracket s, when we consider the relative velocity, c minus v, before passing from alpha to beta. Consequently, the time t subscript L2 square bracket s or alpha cd sub v s taken to pass from alpha to beta at the relative velocity c minus t is equal to, whoa, that's a doozy.
Yeah, that's
T
T sub L2 stationary S times C minus V L sub V stationary S.
we have cursive L sub vs is the number of rest meters in length L sub vs from equation 14. The time for light to travel across L sub 2 can be written alpha cd sub vs alpha to beta equals curly or cursive s or cursive L sub v over c minus v. Multiplying both numerator and denominator on the right hand side of equation 15 by c plus v and using the definition of gamma, equation 15 becomes alpha cd sub v s alpha to beta equals cursive L sub v gamma squared over c plus cursive L sub v times gamma squared times velocity over speed of light squared. Using equation 4 and 16, we get.
Nice. This is delta.
Oh, my bad.
Triangle. You're straight.
Delta CDV or CD sub V alpha to beta equals cursive L sub V gamma over C plus cursive L sub V gamma to the power of V? Or is that times V?
Where at? Right here?
I guess that's times V, yeah.
So
Gamma times
times V. Gamma times V.
Gamma times V over C to the or C squared.
Yeah, so
we have seen above that in equation 17, the length cursive L to the sub V is given using rest frame units. However, the moving observer uses the moving units, which is a number gamma times smaller because the moving standard meter is long. This is so stupid. Okay. Substituting equation 2 in 17, we get delta CD sub V, V alpha 2 or times alpha 2 beta equals cursive L sub V over speed of light plus cursive L sub V times velocity over the speed of light squared. If we repeat a calculation similar to the equations above, when light is emitted from a source at rest but moving in the opposite direction, equation becomes delta CD sub V, V beta to alpha equals cursive L sub v over speed of light minus cursive L sub v times v over the speed of light squared. Equations 18 and 19 show that the time interval for light to travel from alpha to beta is the sum of two quantities. The first term, cursive L sub v divided by speed of light, corresponds to a time interval expected, assuming the velocity of light. The second term must be explained by another phenomena. In order to measure the velocity of light in the moving frame, the observer takes the display on clock alpha when light passes in alpha. Later, when light reaches location beta, he records the display on clock beta. We have seen in equation 13 that clock beta is late with respect to alpha. Consequently, the difference of display between clock alpha and beta after the travel time between the two clocks is given by equation 18 minus equation 13. This gives delta CD sub beta minus, delta CD sub alpha times alpha to beta equals cursive L sub velocity divided by speed of light. What is the alpha to beta? That's just saying the distance there.
Yeah. I would assume.
Gotcha.
I would assume so.
When light moves in the opposite direction from beta to alpha, since clock beta is late with respect to alpha, we see that equation 13 must be added to equation 19 in order to get the difference of clock display between clock beta and clock A after light is traveled between the two locations. Therefore, the difference of clock display between beta and alpha given by equation 13 plus equation 19 gives delta CD sub A minus delta CD sub B times B to A equals cursive L sub velocity over the speed of light. Equations 20 and 21 explain why the velocity of light appears to be c in the moving frame. However, it is an illusion because the real velocity is c plus v. The error is due to Einstein's clock synchronization method, which gives a wrong synchronization. It is very important to notice that this error in clock.
Oh, sorry.
No, you're good. You're good. You're good.
There,
I actually kind of want to read this anyways.
Yeah, dude, it's a doozy.
That last paragraph, at least.
Yeah. So it is very important to notice that the error in this clock synchronization is enormously more important than the usual relativistic correction. For example, in the frame, wow,
You don't say.
no shit, dude. It's a bold claim, Mr. Moore. I'm gonna have to ask you to leave your office permanently. For example, in a frame at a moving for example, in a frame moving at the velocity of the rotation of Earth, which is about 0.000000001 c, this correcting term, cursive L sub v over c squared, is 1,000,000 times larger than the usual correction gamma for the clock rate. Wait a minute, Toby. Wait a minute. Is he saying that the Earth rotating under an atomic clock would be insignificant? Would it be an insignificant correction?
$1,000,000 times larger.
By
It
the way,
is surprising that this term has not been considered previously.
I just looked up what the lowercase cursive L looking thing is, and I dropped it into side chat, and apparently in chemistry it has to do with the azimuthal quantum number, which has to do with like orbital dynamics, allegedly.
Oh.
Huh?
I've never even heard of that before until you guys were just talking about it.
Which one? Oh, the cursive L?
Yeah.
Oh yeah, he's using it for length of the velocity of the thing in motion for this. It's just a cursive L.
I thought it was like a Greek letter or something. sort of like theta or omega or something. I don't think it is.
Yeah, not that I've ever seen. Let's see here. Okay, so see this correcting term is 1,000,000 times larger than the usual correction for gamma for a clock change of rate in the length used in relativity. It is surprising that this term has not been considered previously, while the relativistic term gamma, which is a much less important, which is much less important, about 1 part in 10 to the 12, is taken into account. This paper deals with relativity with this relatively large term, 10 to the minus 6. A detailed study of the other much smaller 10 to the minus 12 term will be fully explained in a future paper that won't be published because I got super silenced.
So, like, is he basically saying that, like, the relativistic effects are, like, don't mean anything in comparison to the actual errors in the clock correction that they have to ignore?
Yeah. So
Okay.
look at this. This is oops, do you want to change? I mean, I hope so. Let's see. Where was my boy? What was I just about to show you? You just asked about the relativistic corrections. Right. Okay, so check this out. Right here. So this is a paper in 1995 that was put out as like a GPS topologist, where people in the field were asking, "Hey, I work in the GPS field. Where are the relativistic corrections at? Where's time dilating? Where's the link contracting? Where's the E equaling squared C's and M's and all that?" And
Yeah.
they came out here, and this is the official publication saying like basically the basically general and special relativity cancel each other out to a degree where only the classical effects take precedence, so they're just accounting for those. In the future, when GPS is going to be more accurate, they'll have to account for those, but they don't do it right now, and those relativistic effects are forthcoming. Yeah,
Dude,
so
so just like if you've dug this deep, we're just gonna tell you that you're gonna have to just absorb special and general and just stop thinking so much about it and just use our reference frame.
yep. Yep. And to end on so this is Carol Alley. This is someone who did an atomic clock experiment that got Einstein clock synchronization to work for 14 hours. So shout out to Carol Alley. Um and then obviously they don't continue to use that, so it's not a practical thing, but they did get a 14-hour experiment under their belt. You can find that on McToon's website. So I am happy to hear Henry. Oh, oops. Anyway, they end here saying, bring it up here. All right. And that if one perhaps does the explicit recognition of the special relativistic effects, I mean, it took a long time to get general relativity down properly, but I think that that it is more or less correct now. But its absence of any explicit acknowledgement of the special relativity effects due to the speed of light being the same whenever measured by an observer, leading to the relativity of simultaneity in the Lorentz transformation, and associated with Lorentz transformation physics. There's nothing of that at all modeled in the current system, and I think it should be. Thank you.
You're out. Get out. Stop questioning our fundamentals. He's like so polite about it.
Dude. So this guy did his clock experiment for 14 hours, which
Poor dude.
and he's like, "Hey guys, it took us a long time to get general relativity predictions
Oh
down to
no.
explain these clock effects." But obviously they don't even work, right? Cuz like they don't even sync them that way. But yeah, this dude was like, "Hey, dude, dude, look at that special pleading, dude. Just like, dude, but in the absence of the explicit
It took a long
acknowledgement,
time to get it down properly.
but we
But
did
I
it.
think it's
Hey
more like
guys, we did it. With Toby, we did it. We detected gravitational
Yeah.
waves.
But this guy, but he's just like, guys, maybe maybe this clock sync problem means something.
Dude, there's nothing modeled in the current system, and I think it
And I
should
think it
be.
should be. Thank you.
You know what? I think it should be too, man. That shit ain't right, bro. You got your boy Ian out here on blast talking about his clocks ain't synced right. I think they need to include it too. So, quick recap, but it's the absence of any explicit acknowledgement of special relativistic effects due to the speed of light being the same whenever measured by an observer, leading to the relativity of simultaneity in the associated Lorentz transformation physics. There's nothing of that at all modeled in the current system, and I think it should be. Thank you. I like that. Thank you, yo, Toby. You like trying to do a reading on this guy, dog. Do a short on this. Like that. Thank you is fucking priceless. I worked really hard to figure out this kinematic math that doesn't do anything and would lead our clocks astray because the real issue is relative velocity being having an effect on the electromagnetic retardation of the light propagation within the moving system. But I worked really hard to do my part of it, and I want you to include it in the framework. Thank you.
Dude, his whole paper is like, so we know this is how relativity works. Here's how we could, mechanically try to explain this situation. Here's how we could explain this and that. Here's how clock synchronization is proposed to work. Here's how we have to sync clocks. And, here's. So he's playing the game and he's playing it so hard. Like he's right in there, right in the mud, right? And he's like, but he's talking about the no topic, but out of necessity, because he's just talking about clock synchronization. And he's like, so he's like, goes through all of it, plays the whole game, and then in his conclusion, he's like, hey, look at the game works so well. I loved the game. This is so cool. But this relativity of simultaneity and Lorentz there's nothing modeled for the simultaneity problem we're running into. I mean, maybe we should just at least model it.
Dude,
Thank you.
how crazy is that it's like this issue doesn't exist in the system and he wants to introduce it to fix it.
Right.
Like, dude, he wants to introduce a method of synchronization where there's no cohesive timeline of events so that he can solve it. It already works without it. There's no need to include it. And he's like, thank you, please include it. That's cool. So, shout out to that guy, Fiegel Henry, and the boys over at the GPS Joint Program Office at the Aerospace Engineer at the Aerospace Corporation. That fucking generic alphabet corporation. Very, very cool. All right. Let's see where were we at? Your boy GPS paper. Oops. All right. So the gamma corrections that they claim to account for don't affect anything at all, and the relative velocity of the craft is what's important. Okay, cool. Cool. Experimental confirmations of the discordant Einstein synchronization method with GPS. I mean, how could you read this and go, yeah, relativity is super like on point? Like, as you're confident, Toby, in
But are you smarter than science?
like Has your confidence? Have you gained any confidence in relativity while reading this? Like, is your position wavering? Like, do you feel like the sweat on your brow, like of an impending, like you're super wrong about your position?
Lose sleep for 3 days.
Dude, like, there is a direct measurement proving that the velocity of light in one direction is c plus v with respect to a moving observer. This discordance. What the fuck are you saying, Paul? You can't say that. Not allowed to say that. With respect to a moving observer, this discordant synchronization is given in equation 13. Oh, we'll be revisiting old equation 13, and the discordant synchronization given in equation 13 has been measured in the world system of clock synchronization with the global positioning system. It is observed experimentally that Einstein's method of synchronization using the half-time interval taken by a reflected light beam is inadequate to determine the correct time. Hold on 1 second.
Good sentence. Yeah. Yeah.
1 second. 1 second, buddy. That's too many fucking. That's too coherent and straightforward. I need more
Yeah.
transformations. Oh, wait, this is actually even better. A Sagnac effect has to be
Yep.
added. So this is going to be super relevant here. 1 second.
Correction.
So I'm going to take this, go all the way up.
Bro had to call it point out that it's the Sagnac effect too.
Yep. So we're about to swoop in on a atomic clock. So where was that half coefficient or the 1/2 thing at? I have to connect these for later. It'll be easier to find in battle. Where was the Einstein method? Okay, hold on. Einstein clock synchronization. Fuck, it's up here. Where is it? It's part of the fucking. Oh, there it is, right there. Okay. All right. Jesus, that's a long way down.
There's a lot of shit getting through those different
Dude,
methods.
yeah, but this is like the super important part, and I will be needing this later. Yeah, damn. All right.
Yeah, I don't think they said the word Sagnac effect once, or the phrase Sagnac effect once, in all the other clock sync examples, did they?
No. But we're about to find out how these equations are hella Sagnac-y, one could say. All right.
I mean, it's like we know just from what we know that like you guys are just describing Sagnac. Clearly.
Oh man, took a long time to get down here to page 7. All right, but it's been a good read. Let's see here. So, a correction, which is the Sagnac effect, has to be added. Now, keep in mind when you start looking into GPS and the Sagnac effect and Sagnac correction, you'll come across the term Sagnac correction. That's not to be confused with the Sagnac effect. The Sagnac correction is a correction that they say that they're applying as a rotational value relative to the latitude on the globe, as if the Earth is rotating out from underneath the electromagnetic propagation or rotating into it. So that's what they're talking about for that. They're not even touching the velocity proportional relationship or anything like that. When they say, when they talk about that Sagnac correction, they're referring to Earth rotation. The Sagnac effect is in relation to a proportional velocity and a length of propagation for light. So those are the two primary factors in determining a Sagnac effect. So that's a huge distinction there, because it may look like they're the same thing, or you might assume they're the same thing. They're not.
Now, Sagnac correction, that's specifically referring to the drift in the light propagation rate,
So in
or is it relating to like the GCS?
So in 1995, there was an experiment done by Allen and others, and they basically used the GPS network as a giant interferometer, and there was a variance in the speed of light measured in that, and they attribute that variance to Earth rotation.
Okay, so in the actual, okay, got it. Thank you.
Yeah, but obviously we know what's really happening: ether wind, relative velocity proportional relationship due to the ether wind, etc. Right? But this is the mainstream steelman of their explanation of why there's a variance with the clocks.
Wait, so where is that data stored?
What's that?
The Sagnac corrections, the Sagnac correction data, that all goes through I guess that's all happening through GPS, right? Through their GPS database somewhere.
Yep. So there's this paper in 1995 by Wolf and Pettit, and these guys were analyzing GPS data from a server to analyze the speed of light, and what they found was that there was a correction that was applied to their data set before they could. So they thought they were analyzing like a raw data set, and then they realized it was already pre-corrected to adjust for Sagnac corrections.
Oh,
so like,
isn't that
so
fucking fun?
Yeah, so like from the transformation, so this is basically what would be data from the transformation from the ECI reference frame to the ECEF.
Yep.
So the variance there, they're saying
And
that
extrapolated onto the global coordinate system.
right. So
Or-
they're
yep.
right. So they're looking at a variance added there in the data, and then they're just like they don't mention the implication there, but there was a guy named this guy right here, Daniel. Should have him in here. Daniel Garzi. So this guy's a beast. So experimental basis for relativity, special relativity in the photon sector. So he points out this analysis from that Wolf and Pettit guy. Wolf. Let's see. So I'll just read it here. So the classic resonance cavity. Hold on one second. So the classic resonance cavity speed of light isotropy experiments, e.g., Cedar-Holme and others, 1959, Brillet and Hall, 1979, and have been recently repeated, have significantly improved the upper limits, and they have been sent to Koskela and Muse in 2002, and Baxemeter and others in 2002, and Mueller, not to be confused with Miller, Mueller and others in 2003, Mueller again in 2005, Mueller and others again in 2006, and then the Wolf guys. The isotropy experiments would be the same, which concerns to the. Where's the? Hold on a second. Where is the? Sorry, I was wrong Wolf.
You're good.
Okay, so right, we're okay.
I'm reading this too. That's interesting.
Yeah, we're on the correct Wolf now. So one of the most familiar arguments for the validity of special relativity is that the global positioning system, navigation system, would not achieve high accuracy without making special relativistic corrections. The principal correction cited is a first order timing adjustment to compensate for the signal propagation time variation arising from the motion of the satellite and the ground receiver in the local Earth-centered, Earth-fixed frame, due to the Sagnac effect. But the Sagnac effect is a purely classical first-order effect and has somehow been incorrectly misclassified in this application as a special relativistic effect. See Allen and others, Weiss and Ashby. So these are the guys that. Oh, I'm sorry, that was in the 90s or 80s. So this was the around the world SAGNAC experiment where they turned the satellite system into a giant interferometer. So this was these lads, and then this Ashby guy went around for the next 20 years, saying, basically putting out this narrative that the Earth rotation needs to be accounted for, SAGNAC, like this is where that whole narrative comes from. That there's a velocity correction from, uh, that this was discovered from him and all that, right? So the narrative about the variance being due to the rotation is from this guy
Gotcha.
in this experiment. So the first order timing correction must be made for the accurate performance of the GPS system, just the amount attributable to the velocity component of the satellite constellation along the line of sight in the ECI reference frame. Holy shit. What did he just say? Attributable. Did he just say that the velocity of the craft is what's being accounted for?
Yeah, it is what he's saying.
In plain ass English? I didn't even realize that the
Just the
first
amount of
4 times.
attributable to velocity component of the satellite constellation along the line of sight in the EC, like in the ECEF frame, so like in his lab frame.
Man, dog.
So that whole paragraph is like pretty dang straightforward.
Super straight. And then, so that the fact that a first order timing correction is required at all is in direct conflict with special relativity. Oh no, nothing to see here, or whatever, dude. The speed of light's the same. Okay, so then Wolf and Pettit, 1997, tested the isotropy of the one-way speed of light by analyzing the GPS satellite network timing signal database and found no dependency on the source receiver's motion, which they interpreted as evidence that C was isotropic. However, Wolf and Pettit noted that the dataset they analyzed had been pre-processed and corrected for the SAGNAC effect. In this case, a first-order change to the time of flight to the radio signal between the satellite and the receiver, and justified making this correction by claiming that the SAGNAC effect was a relativistic effect that was second order in C, and therefore made the correction negligible, and therefore that the correction had a negligible consequence on their analysis. But the correction that was made was first order in the velocity component of the line of sight between the satellite and the ground receiver in the ECEF frame. Thus, while the effect of the first order line of sight velocity component of the GPS satellite is clearly evident in the raw timing data, the first order component had to be removed from the data set that Wolf and Petit analyzed to show that C was isotropic.
Wow.
Boom. Oh no, dude, what did he just say?
Okay, so those are the dudes that were doing that, that were looking at the data. Okay, wow.
So this right here, so you know how we were saying earlier that in the documents they say there's a variance in C proportional to the velocity of the observer. Well, this SAGNAC correction, he's saying would have he removed that in the data that's on the server, bro.
Yeah. Which is so sus when people like we know it's an effect. So why do you have to remove it?
Like, dude,
are you hiding something? Maybe,
dude. That's why
I about it.
Totally forgot about this.
The truth about our actual globe or our map, our Earth, like the actual map data. I mean, specifically related to the ether wind, but like there's so much information hidden in those corrections. Like information about the ether wind, information about the actual map shape, and then of course just utter wreckage of relativity.
Oh man. All right.
Who owns that data? Where is that data at?
Let's see. So, I wonder if they say where they got it. I don't know. Oh, okay. So, I don't know. We'll have to read it and see where they got the data. All provided by the NASA Astrophysics Data System.
So all these transforms, like I want to know where this. So what was the data set called again? I feel like it had a name, didn't it? I guess just the SAGNet corrections. But where is the SAGNet correction database?
Oh, it was so however, Wolf and Pettit noted that the data set they analyzed had been pre-processed and corrected for the Sagnick effect. So oh my god. Dude. This is oh my god, this is so bad. This is actually what you would call the smoking gun.
Yeah.
That proportional velocity ship relationship is like this. It's like, dude, the speed of light changes, bro. Like, GG, get the fuck out of here.
Well, and like
there's
that
no way to
specific database. That specific database is gonna have everything too.
Yeah, whatever they analyze, we'll have to get the specifics on it here.
Instead, the correction is integrated into the algorithms and operational software of the GPS system. No central database. What?
Usually they have like a thank you at the end. Acknowledgements. The authors are grateful to Dr. C. Thomas and Professor Gibbs for help with discussing. There is a Blackburn for the manuscript. Ocean Tides. Yeah, it's unfortunate. I'm sure we'll be able to figure it out. Where the data came from.
What's going on, y'all?
What up, dude? Just doing a little GPS review here to make sure that the speed of light is or isn't the same in all reference frames.
Any solid evidence?
None that supports that it's the same.
Perfect.
Yeah. All right. So that was cool for the SAGNet corrections and all that. So yeah, that variance proportional velocity relationship, they just erase that and say that it's a Doppler effect.
Hey, what's that paper called, real quick?
Yep.
The last one you're just looking at.
Yep. It's called
Relativistic Theory.
Yep, I put it in live chat.
Clock sync.
And you're definitely going to want this one too, because he goes over a bunch of other experiments too, and just like bangs them out. So, and this guy was published in Cornell as well. So like, if anyone's like, "Oh, where'd you get that?" Like, buddy, like this one says from ResearchGate or whatever, but it's literally on Cornell's website too.
Sweet, thank you.
So this is an act or I forget where he. I think he's like a professor or something. Yeah, Goddard Space Flight Center, Doctor of Philosophy. Yeah, he works at NASA. Hey, you want to come on in the field?
Something tells me.
But yeah, shout out to this guy. Just straight up put it out. And I mean, this is devastating, dude. So like now we know like the Sagnick effect. What is it? What does it mean? Proportional velocity relationship to, to, and then the distance would be the distance for it took, or like the time it took for the electromagnetic propagation to go from the satellite to you, and then then your velocity somehow affects that proportionally. How do you think it does that, Toby? Do you think there's some sort of background medium?
Oh, dude, no, it's what do they call it now? A Higgs field.
It's a least squares regression geometric field of abstraction.
It's funny. I read that last sentence of the first paragraph, and I was just thinking, I'm like, wait a sec, because I saw second order in C. I'm like, wait, what the fuck, second order? And then I read that last part, and it's like the fact that this first order timing correction is required at all is in direct conflict with special relativity. And I was like, that's exactly what I was thinking.
Yeah.
Yep, you're
Yeah.
reading correctly.
Yes, sir. Yeah, man, it's just devastating. So yeah, I kind of forgot about this
Why is there a
supplemental
first and
argument.
second order of C? Isn't it a constant?
How dare you?
Dude, you're gonna lose your desk. You're gonna lose your office.
Oh, bro, you know what? Hey, Beasticles, you know what happens when you start talking like that, bro? Someone comes to you in French and says, "Ce n'est pas ton be tu consider ton problème el esto tu remanentes question de la principles fondamentales de la physique." Right? So when they come and say that shit, you know what that means, bro? This is not your office we have a problem with, or it's not the office we have a problem that we want. You're the problem, and the problem is that you're questioning fundamental physics, principles of physics. So,
Where did you get this from?
the guy that wrote this paper explaining how Einstein clock synchronization doesn't work with atomic clocks and how the clocks actually account for the Sagnac effect got super fired. I'm explaining. So,
you got that from the paper?
Yeah. So this guy got fired, and then we were looking into that situation or whatever, and from where was that from? From the from the website here, it has a direct quote of the head of the physics department coming into Marmot's office where they're firing him over this paper. And he said, that French stuff to him, which says it's not the office that's the problem. It's you keep questioning fundamental physics. So get the fuck out. So 3 months later, they sent a letter to him requiring that his office become unoccupied at the end of the month without a research grant and being expelled from his office. Dr. Marmont continued his research alone at home. Sucks, bro. Shout out to him.
Hey, is he alive?
Negative. Ghost Rider died in 2005.
Damn.
Yeah. Died to complications due to bone marrow cancer. Damn.
Ooh. Let me switch to my phone. I gotta get more cigarettes. Excited for tomorrow?
What's that?
Ether Roundtable.
Oh yeah.
What's the plan for tomorrow?
We got a nuclear engineer coming through to do a little Q&A, tell us about his mass energy relationship. And then we got we're going to be doing a live reading of some of the Wang paper.
Nice.
Yeah.
I want to get in contact with him, dude.
With Wang?
Yeah. I want to get him on.
Yeah. Yeah, I doubt he'll talk to us, bro. He holds a patent for technology that should not exist.
What do you mean?
He invented an interferometer that measures absolute motion with no external references. And if you mount 3 of those in an XYZ axis, you can measure absolute motion in 3-dimensional space with micrometer precision.
Yo, I'm back.
And he has a patent for that type of technology, but it doesn't exist.
No, it's not supposed to exist. It's not supposed to because of the principles of relativity and all that, blah blah blah. Like, you're not supposed to be able to measure absolute motion because that would require an absolute background and all that. So if you're going to measure something, the measurement of the speed, has to be relative to something. You have to get external sources, blah blah blah, right? So he uses like the absolute background and the variance in C to derive velocity without any external references.
Wow.
So like linear motion, acceleration, rotational, it doesn't matter. Your boy can detect it.
Yeah, the timeline goes 2003. He does experiments and figures out that basically motion is completely detectable with linear interferometry, even linear motion. And then January 2004, he immediately puts in for a preliminary patent to patent this speedometer design. And then 2004, he does more like multi-million-dollar experiments with government funding, doing more testing with the exact same type of interferometry. And then 2009, his patent is finished. And then, well, I was going to say he kind of disappears and stops talking about it, but he just released a paper this year talking about it.
Yeah.
Shit. That'd be the perfect time to get him on. Oh, I'd like to talk to you about a new paper. All nonchalant.
Yeah. Yeah, I want to try again, man, and to try a different approach. Be like, look, Wang, let's cut the bullshit, guy. I know you measured absolute motion, and I know you were paid as fuck. Do you want to come tell us about it? All right. So yeah, if you ever get someone at your door that starts speaking in French, they're probably accusing you of this and firing you. All right.
Light drag effect on vacuum tube versus light propagation in stationary vacuum tube with moving source and receiver. Dude, he still has been doing like. This looks pretty interesting too.
Oops, it's the wrong one. Light drag in a vacuum tube. Oh yeah, I think did I download that earlier? Recently added light drag in a vacuum. Is that the new one?
This one's 2016. The other one is newer.
Okay, yeah, I got the 23 one. All right, cool. All right, let's finish out Marmot here.
Okay.
All right.
My bad.
You're straight. So okay, so we learned that the Sagnac effect, two important factors, your velocity and the length of propagation are the determining factors for the variance in C. As an example, let us assume a clock alpha from figure 2 is in New York. And clock beta is in San Francisco. As illustrated in figure 3, the velocity v is the velocity of the rotation of Earth around the pole axis at the location where the experiment is done. The distance, cursive L, is the distance between New York and San Francisco, the dotted line on figure 3. After the initial synchronization of clock alpha with a mobile atomic clock called mu, that clock is moved from New York to San Francisco at a constant altitude and slow velocity epsilon, see figure 3. The constant altitude at sea level avoids other corrections due to gravitational energy, which
gravitational energy, huh?
Yeah, dude. So that's you can't forget about your special relativity effects, my dude. So
funny how they ad hoc in Pound Repka for that. All right, continue. Sorry, my bad.
Yeah,
I don't want to derail.
It's all relative, bro. It's all related, though. It's all relative.
So silly, dude. They just ad hoc it in when they want.
Like just in case that gravitational potential changes, but they do measure like that variance in C at altitude. Like there is a change, right? So and what they do have, there is the downward bias, so there is a thing to correct for, but it's just not there due to the what they think it is, right?
Yep.
So let's see. So assuming he's flying at that constant altitude to eliminate that variance, which would be irrelevant in this paper, the equivalent of such an experiment has been done by Sadith and others in 1986 using a truck containing a number of atomic clocks previously synchronized. Oh, I haven't heard of this. This is a new thing to look into.
A truck containing a number of accurate atomic clocks previously synchronized with.
And others. Okay, so Sadi and others, 1986, using the clocks containing an accurate number of clocks previously synced with the primary standard of time. In the truck, the clock moving west or sent across the United States. This experiment is reported in Science Astronomy 1991. Wow. Definitely. Hold on a second. I'll do it later. All right. In the truck, moving clocks. Okay. Okay. Using the GPS. What are we about to learn from this? Using GPS correction, which is mathematically identical to equation 13. The correction time between New York and San Francisco is set up between the clocks alpha in New York, alpha in New York and P or beta in San Francisco. So let's see. This experiment is reported using the GPS correction. Oh, okay, my bad. I thought he was saying that was. Never mind. Okay. Let's see. Clock synchronization of the rotating Earth. So we got your rotating Earth from east to west here, right? Or no, because the Earth is going this way, right? Yeah, going this direction. Left to right, left to right, and then we got New York and San Francisco. The dotted line is our distance. He's saying that we sync up the clocks how we did earlier with the.
Wait, no, isn't it rotating the other way? Did I mishear you?
No, it's rotating west to east, right?
Yeah, west to east. Okay, yeah.
Yeah, so from the left to the right. Like, yeah, he has arrows here. So that's cool. I didn't even notice the arrows the first time I looked at this. Very cool. All right, so let's see. The reader must be aware of the fundamental principles of physics involved with GPS, the standards of synchronization of clock stations used by the Global Positioning System have been published in 1990 by the International Radio Consultative Committee, International Telecommunication Union, or otherwise known as the CCIR. 19.
Did you ever look at that one?
What's that? This right here? No.
Yeah, that would be interesting to look at too.
Yeah, add it to the list.
Because of the standards for their syncing process.
Yeah. Well, I think he goes over it here.
Oh, okay, gotcha.
So let's see. So the global positioning system determines that after clock moves away from clock A in New York towards clock B in San Francisco. Okay, so we got a clock here A, we got a clock here B, and mu is traveling in between. Okay, away from clock towards it. It would gain an extra 14 nanoseconds approximate. So the mu clock would gain an extra 14 nanoseconds approximately with respect to clock beta. We know that due to the Earth rotation between New York and San Francisco, clock mu moves at velocity minus epsilon, which is the velocity of the rotation of Earth, v, minus the velocity of the truck, epsilon. Therefore, 14 nanoseconds are subtracted to display at its arrival in order to correct the synchronization of the clock B in San Francisco. This correction is identical to equation 13. Literally, god damn. All right.
Wait, so
What's equation 13?
Equation 13 is the Sagnac is basically accounting for the Sagnac effect. So the velocity of the observer and the length of time, or the length or time of distance traveled.
They use two clocks to synchronize it between San Francisco and New York.
Can you scroll back up to the diagram real quick?
Mm-hmm.
Is mu on here?
It's traveling along the dotted line. So like mu
A and B are fixed.
Yeah.
Or alpha and beta rather. Can you scroll back down again? I want to read it again now. Sorry.
Yeah, let me draw a little.
Yeah,
that didn't work. But I was gonna draw a little mu, but that looked like shit.
The term clock keeps throwing me off because I think of like an actual clock, but like it's really what they're talking about is
the oscillation rate of these clocks.
On the
So-
satellite specifically.
on the
in
satellite
that- in
specifically.
this
So
particular case.
okay, yeah. So you know how we were saying earlier that an atomic clock, like they say like, oh, it's a uh they attribute it to like it's a particle, right? Like a cesium clock, right? But it's just it's a frequency of radiation, right? So they have a specific frequency that has a specific oscillation rate when it's excited, and so they're saying that there's a vibratory rate of 12 billion oscillations per second, and they keep that. They use two magnetic fields, two counter rotating magnetic fields to like maintain that to maintain the electromagnetic retardation of that oscillation rate. And then when there's energy loss like in that system, or it starts to go out of sync, they'll shoot radio waves uh at the detector. At the cesium to like re-excite it so that its energy output maintains that
22 million
that
oscillations per second.
that 12 billion oscillations per second.
Well,
And
yeah.
then and then so the corrections so like basically, Toby, if you think about it, like it's almost like an interference pattern. So it's like it's only accepting a certain fringe shift, and they have to make corrections to keep that fringe shift in line. You kind of think of it like that, or
Yes.
I
So a
do.
correction for the frequency.
Right.
Okay,
It says
okay.
consequently, the Einstein's clock synchronization method compatible with the time given by the GPS, and the Sagnac effect must be added.
Yeah, and so then the Sagnac effect again is basically they're saying, oh, so basically special relativity says that the speed of light is the same for, inertial observers, and here we're looking at a variance in the speed of light that's proportional to the velocity of the observer, which is like the exact opposite of how they say relativity works. So they built an entire framework on the opposite effect, and then now they have to account for it in GPS without admitting it, and like we're going over the how they're covering that up. And this guy totally exposed it and got super fired over it.
The global positioning system determines that after clock moves away from clock alpha. So that's as that frequency or that frequency is moving away from clock alpha, it's accumulating nanoseconds on the frequency.
So so the time difference they're saying, if they were to add it up, like say you were to say you were to shoot electromagnetic propagation from New York to San Francisco, he's saying that the equivalent of what happened was that it was C plus 14 nanoseconds.
All right, scroll back down again.
Yep.
Thank you. Sorry.
And basically, in actuality, it's actually a variant of the speed of light. They just say like, oh, well, we're subtracting 14 nanoseconds to the display to give the synchronization
to attribute it to Earth rotation, or like to disguise it as Earth rotation, but really the equation accounts for the velocity of the observer, right, or of the thing that's carried. So in the instance of an atomic clock on a truck, the
Right.
the motion of the truck, because the atomic clock's on the truck.
Okay, so here's where I think I'm getting confused. So when it says the display, that's the result that we're getting from the ground.
Therefore,
the display at its arrival. So that's talking about truck. It's talking about the truck. So basically, the person in between A and B.
Or alpha and beta. Okay, so
yeah, Toby, you remember how they had to send this clock didn't activate until it got a signal from clock A that had its time encoded, and then it would
Yeah.
activate with that time. So they're saying basically they had to send like a compensation in with this signal so that it would activate minus 14 nanoseconds so that it would display the correct time on its on the display.
Oh, okay. Okay. It's display. So what is the display means?
Like
I
if you
keep
were
thinking,
if you were looking at a physical atomic clock and it was like giving you its outputs, like the display reading.
Right.
but on the satellite itself.
Well, these are atomic clocks on a truck, but yeah. Like they would just have a onboard computer, do it for the satellite. But yeah,
Just
See, that's the part right there. When a clock moves eastward, we understand that the velocity of the clock is added to the Earth velocity, so that the term uh becomes larger. I don't know what that is for the
oh
moving mass. Ooh. Then for
wait.
masses A and B, which do not possess that extra velocity, consequently, the clock moving eastward runs at a slower rate.
So the clock literally does run slower.
It says it right there. Consequently, the clock moving eastward runs at a slower rate because it's traveling along the preferred direction of light.
no, it travels faster, but their interpretation through this is through Earth rotation, so they are interpreting it backwards.
Hmm. But that's physically what happens. The clock literally does do that.
It gains speed. Yeah, that's what they measured in Heffel and Keating, but the clocks didn't go out of sync or didn't adhere to Einstein's clock synchronization, but they do show that a variance.
Is that directly proportional to Sagnac effect or
Says
Sagnac
it.
corrections?
So I don't know how the clocks were actually synced in Heffel and Keating. I would assume that they did it to the method of Einstein. So it would have been synced to that using that equation, using what would essentially be equation 13. So it must have
Yeah, it says it right.
so the fluctuations. That's super perplexing then because it would have been, but the two of the clocks going in the opposite direct or gain time when they were supposed to lose it because there was four clocks in the set. So when they're all supposed to gain time, two of them lost time. And when they're all supposed to lose time, two of them gained time, and by amounts that made no causation correlation to anything. Like the synchronization was all over the desynchronization was all over the place. It actually the because it was outside of the predicted results by such a degree, the experiment was a complete wash. It wasn't until 1972 that they republished their data, with corrections and said that it showed a that it supported Einstein clock synchronization, but obviously it doesn't, right?
Yeah, it says it right there. We see that the GPS correction of clocks 24 is identical to the Sagnac effect, but also perfectly identical to equation 13.
Yeah,
Wow.
so they definitely accounted for it. But yeah,
Right there,
they're
yeah.
Pretty interesting. Okay.
yeah.
Thank you.
Yep. So experimentally, an equivalent experiment has been done carrying a clock between Washington and Tokyo in Saburi, and others. Let's see, 1960 or 76. It is then an experimental fact that the two clocks A and B are naturally synchronized at the same value as the result of the discordant Einstein clock synchronization method above. There is another well-known way to synchronize the clock of the two stations alpha and beta. It is done by sending radio signals transmitting simultaneously east and west and east between two cities. Again, it is observed that a simultaneous transmission of the radio signals between New York and San Francisco does not give directly the same correct clock display time in both cities. There is a difference by about 14 nanoseconds that must be subtracted to the clock from
In
San
San
Francisco.
Francisco.
Yeah, in San Francisco, in order to get the correct GPS time. This correction is identical to one when we're carrying the clocks. The correction corresponds to the change in the velocity of c plus v between the stations.
So they're basically comporting velocity with Earth's rotation, but what it really is showing is like that that if you send signals east to west, you're kind of going with that ether wind kind of thing. Is that what I'm picking
Yeah,
apart? I don't know.
yeah, that the speed of light isn't the same.
When going east to west. I
Yep.
mean west to east.
Yep, and it varies by the same like by an exact amount. So it's not like there's like an anomaly. It's like an equal resistance potential situation kind of thing. You know, like it's catching a boost
Right.
by the exact amount that it's also resisting in the opposite direction.
Right. And it's always that fact. Going east or west to east, right?
Yep, and they'll do it. So even when the Earth isn't, I'm sorry, even when it's not like electromagnetic propagation not attached to the Earth, even when they have ground cables in the Earth,
Fiber optic,
there's a literal preferred direction as
right.
well.
Even with light pulses, which
Yeah.
are basically the fastest way of communication or sending data.
Yep.
Right.
Yep. So let's see.
Unless they have a faster way.
Yep.
I don't know. That's interesting.
Yeah. So GPS synchronization has been verified in numerous experiments. It is identical to the calculations presented in this paper, and also to the Sagnac effect, which is included in the GPS. Among the list of the corrections, there is a correction involving a parameter taking into account how many Earth meridians are crossed by the path of light or by a moving clock move between the what?
Wait, what?
What?
Are crossed
Yo.
by
Yo.
clock.
Whoa. Whoa. Red
What is the Earth
flag.
meridian again?
Red flag. So the latitude line. So every time it crosses the lines, like
It says
right
there is
here.
a correction involving a parameter taking into account how many Earth's meridians.
So anytime it crosses one of these lines, Toby.
There's another account for it, right? Another parameter that they add into it.
Dude.
Go back.
Dude, Toby, we're never gonna be able to get the distance using GPS, dog.
No, of course not, dude.
No, look
course
at this.
not.
Literally to the fucking meridian, bro.
Among the GPS list of corrections, there is a correction involving a parameter. There is a correction involving a parameter taking into account how many Earth meridians are crossed by light. Dude, wait. So GPS signals are based by numerous experiments and identical to the calculations. Where can we find? Where can we? Can we pull that? I would like to pull that other one up at some point. Maybe I can pull it up on my own.
The clock
I want to see
synchronization
this.
thing.
I want to see that, but we're never going to see that. They're not going to
The
show
clock
that.
synchronization. Oh my god, dude. No, we have to go look right now. Because if that's in there, what was that document called? I highlighted it in green.
You had it marked at green, yeah.
Yeah, it's
Go up, I think. Oh wait, no.
down here.
I think it was towards the top. I thought.
There it is.
No, that's the truck.
not that one. That's close though.
There it is.
This one right here. Yep.
Yep.
We're gonna go pull this up.
Like if we can find that, that will be pretty cool.
Dude, correcting to the meridian, bro. Get the F out of here. You could never, ever say anything about, oh, we use reciprocal GPS angles. Sorry, buddy. This isn't gonna be it. Hold on. Why did it copy the whole goddamn thing?
I would just do 1980 and then the name of it.
Yeah, trying.
CCIR. So CCIR 1980 basically.
Yeah.
That'll work. Oh, that was it right there. Go back.
Oh, where?
On the bottom right there, reports of the CCI right there.
Where?
1990.
Oh.
That might be it.
Not bad. We're looking for a 1980, I think, but we'll let that marinate for a second. See if we can get. Oh, I put 1990. Oh, Wait, we were looking for 1990.
Yeah. No, 19. Yeah, it is 1990.
Yeah,
Yes.
1990. Wait. So it's which uses
Yeah.
similar rules as the 1980. Actually, so either one.
Okay. Nice. Hell yeah. That's what's up. This must be a
Damn.
beast of a document.
It's probably all the international standards or rules. Oh, yeah.
700 pages. That's what's up. Give me that shit. Give me that document. All right. What is this fucking thing
So
called?
let's look for the word latitude in there
Yep.
or meridian.
Yeah.
Go scroll down a bit. I saw something interesting.
Hang on 1 second. Okay, what was it?
Scroll down. One-way speed of light using global position. What is that?
Probably Stephen Gift. Yeah. He's I got his paper here. It's on the list to go over.
Got all these
GPS.
freaking papers,
That's okay.
all just saying the same thing.
Yep. Yeah, so let me get this documented real quick. Who's the author of this? Oh yeah, these guys.
Düsseldorf.
No, the this committee here. The old radio committee.
The old radio committee sounds like a trustworthy source.
Yeah.
Dude,
That's a beefy one.
Yep.
I'm excited to get into this one.
Yeah.
Dude.
We'll add this to the GPS list. All right, then we'll close.
I need to get my own copy here. What's it called?
All right. Let's see.
Control F.
What would we be looking for? Let's see if we can get even a more precise correction. So, what kind of correction is he saying? Okay, in the track the clock. Okay, the second equation. Okay, the standards for clock synchronization used by this is blah, blah, blah. Okay, well, where did we see that meridian thing? That's crazy.
Up.
Oh, it's up here.
Up. Right there.
Yeah. Okay, so the synchronization. Okay, so we'll just look for
Meridians.
Let's see. Meridians.
I think would be a good one.
Yep. Try here in a second. Meridians cross by. So we'll go. No.
Go back to the red. What's it say? 1990 something? Oh.
Whoa. Let's see. Contours of the constant polarization orientation epsilon with respect to the plane, concentration, local vertical, 106 southwest, okay, meridian plane. Okay, if the effect of the polarization plane geometry, some fixed satellites, utilize polarization, blah. Okay, the curvature of the Earth, this optimizes, okay. Only meridian in here, okay. That's not gonna.
Attitude control corrections. Gotcha.
Wait. Hold up.
What's up?
What the hell does that say? The situation is aggravated by the separation of the beams if the master beam and another beam are both near the edge of the Earth's disk, but nearly opposite direction. What is this talking about?
Beacon tracking techniques can be successfully reduced to point error significantly less than 0.01 degrees of an antenna subsystem. For example, a fixed mobile system multi-beam antenna system by the Japanese ETS-7 satellite achieved, or 6 satellite achieved to schedule. Who knows?
But Earth's disk is an interesting terminology for sure.
Yeah, but nearly opposite positions with respect to the Earth's center. think it's talking about the beams, like that. I guess Earth's disk, the outer edge of a beam. I
Yeah.
guess.
What would the clock sync?
Go back to the red you highlighted. It said something 1990 in the other paper.
Hold on. Table of contents. So plain volumes, contents, deleted. Let's see, performance availability, frequency, data general performance, hypothetical characteristics, ability of circuits the effects of the Doppler frequency shift and discontinuous. Okay, we'll take a look at this here in a second.
Radiation diagrams of antennas for Earth stations in the fixed satellite service for use in interference studies for the determination of a design object. No.
What is this called?
Uh,
Thought I found it, but I don't think I did.
It's called the
There we go. What's it say? Kelly, 1996.
Oh, this is a different paper. I have this one. It's in reference to the clocks, basically saying the same thing about the Sagnac effect.
Gotcha.
International Telecommunication Union, CCIR.
Not seeing any sort of clock synchronization method.
Which volume? Does this a volume number? Does this have a volume number at the start of it?
Yeah, this is volume 4.
Okay, I have 3, 2, and 1. I think they're all 1990.
Can you send them all and look for clock synchronization? Control F clock or synchronize or something like that. See what you get. I don't even get anything for sync. Well, I get a couple syncs, but synchronize. Okay, so the synchronize of the loop. Okay, variable information for transmission rate. The signal for satellite communication.
You drop 4 into chat. I'll drop the other one, the ones I have.
I can drop a link. Yeah.
It was the other one, I think.
Oh well, yeah, it was. You're right. Thank you. It was this one, Toby. Oh wait, no, go back.
Zoom in. No, it's bit synchronization. Considering. Wait. Oh, here we go. What is that? The difficulties can arise from the use of terms. Teletype circuit? No. No. I should be helping you look. I'm like laying down.
It's all good. I'm not seeing any Anything relative to what we're looking for?
Yeah, me either.
International roller nerds. All right. Let's see. Oh, I did want to go look at the Doppler shift thing real quick. The Doppler shift and frequency shift and swifting discontinuities in the fixed satellite service. The fixed satellite service is a received signal subject to the following phenomenon. Doppler frequency shift is due to the relative velocity between the satellites and the Earth station. Discontinuities of the transmission and delay of the Doppler shift is due to the respective difference of the wavelength or lengths of the radio paths and in the different relative velocities switching from the one satellite to another. This report considers the probable magnitude of these phenomenon and their effect on various types of communication signals. Doppler frequency shifts. The magnitude of the Doppler frequency shift between the terminal systems and the fixed satellite depends on the wavelength used and the relative velocities of the satellite with respect to the Earth station. The major component of the effect of the Doppler shift, i.e., the shift in the carrier or the reference frequency of the transmission, can be removed in the receiver. However, it may be necessary also to compensate for the differential shifts across the radio frequency spectrum of the signal that produces a frequency stretch or shrinkage of the baseband signal, depending upon the relative locations of Earth and in the orbit of the Doppler shift transmitting blah 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 blah. So basically, they're saying there's a proportional relationship with the variance at speed of light. Cool, cool. All right, band relationship, calculating Doppler shift frequencies over the band of the. Okay. Altitude, approximate altitude.
Wait.
So, time division, multi in a time division multiple axis system, all Earth stations transmit the same nominal carrier frequency. This requires that the transmitter carrier be only on the interval of the frame assigned to the station. During the transmission, the character. I don't care.
To accommodate this shift, the Earth station receivers must be capable of adjusting to sudden changes in carrier frequency which will occur. This may impose a requirement for increased interburst guard time and for more time within the burst to be allowed for the carrier recovery and burst synchronization for satellites in a non-geostationary. Huh. Fuck is a burst synchronization?
It is. Okay.
Is the burst synchronization what you were talking about earlier?
So no, I don't think so. I don't think so. He probably would have used that terminology.
Maximum daily variation of longitude due to eccentricity and inclination of orbit. Okay. So this is still talking about deviations from orbit, I guess. The consequential error in longitude must be reduced to an acceptable value from time to time, and an accuracy of perhaps a few hundredths of a degree could be achieved given daily corrections. However, correction at this frequency raises technical difficulties, since it is necessary to establish orbital elements after each correction to measure the effect achieved. An accuracy of 0.1 degrees, involving corrections perhaps every few weeks, without considering the longitudinal effects of orbital eccentricity, should be readily achievable. Thruster execution errors. Okay, never mind.
Wasn't what we thought, or you didn't find what we were looking for?
They're just talking about like orbital period variations here. Yeah, it's not like the transforms like we're looking for. But I'm like also just wondering like, would they just stick it in here somewhere and say like this is what we have to correct for, even though it's like clearly not
Dude,
related at all?
that would be so crazy, bro. Like that's what I want to see, where they're just like, yeah, for every meridian line, we chop off this much, and that
Yeah,
would,
right.
because that's just pure distance, right? Because that's GPS is a time interval system, so that distance it takes for that signal to reach the receiver is how they're getting their distance. So if they're making corrections to it to fit their coordinate system, like that's how you would do it. Like that's like we. I'm looking forward to finding their correction, but just Marmot even stating this in his paper and explaining it is GG,
Yeah.
because that's exactly the mechanism what we're talking about when we're like, hey, they could be doing XYZ behind the thing. Oh well, it turns out, the exact mechanism is this, and that's
Dude, so you're trying to find that list of corrections
yeah,
with that parameter,
yeah,
essentially?
yeah, yeah, that would be cool.
I would just type in Earth meridians GPS. I would just do that real quick. Might find something.
Meridian GPS corrections. Okay. Why GPS references the meridian line 100 miles east of the parent? Is this a good? That's not what we're looking for. Let's see. GPS alignment.
Oh, right there.
Abstract. Since the advent of the global positioning position, geodetic azimuths can be geodetic azimuths can be accurately computed by the implementation of a well-known 3D conception. However, GPS alignment surveys involve azimuths. However, when GPS alignment surveys involving azimuths are designed in advance, the later observed and reduced, e.g., during kinematic GPS work, corrections due to the convergence of the meridian should be kept in mind and not ignored. In the study, the practical algorithm was used to compare accurately determined meridian convergence against the classical formalism available in standard textbooks. The typical approximation formula available in the literature was found adequate for GPS engineering surveys, such as airport runway profiles, alignment to power lines or conveyor belts, its stake positioning in highways, constructions, etc., etc. Practical GPS survey was used to collaborate the results. Results finally a new 3D alternative for computing the meridian convergences, which is equivalent to the rigorous formalism. Okay. The globular body. On a curved surface, the globular body. Oh my god. Let's see. So determine the most general applicable employ the geodetic.
Like ellipsoid transformation stuff. Let me see.
Who knows?
Coverage areas of satellite antennas.
So I think basically it's just making sure that it matches their ellipsoid model, really. Yeah. We'll figure that out later. All right.
Yeah, no.
So let's see. Kelly explains that the correction used by GPS is GPS correction equals 2a sub e, which is I think the circumference or the area of Earth. I think it is, and then over the angular rotation of Earth divided by c squared, where omega is the angular velocity of the rotation of Earth. A sub e is the projected area on Earth on the Earth equator plane. Wait a minute. Earth, A sub e, is the projected area on the equator plane of the path used by light or a slowly moving clock between stations. We define cursive L as the distance between the two stations, the both moving at a velocity v. The circumference of the Earth, called circ. Therefore, the area A is A sub e equals cursive L over circ times pi r squared. The angular velocity, or the angular velocity w, or omega, is equal to velocity over the radius. The circumference of Earth is 2 pi r, or the circumference of Earth is 2 pi r. The equation 23, equation 23 in equation 22 gives GPS correction, cursive L v over c squared. We see that the GPS correction of clocks 24 is identical to the Sagnac effect, but also perfectly identical to equation 13.
It's like none. It's not even. It's never surprising anymore to hear it.
Yeah, exactly.
Old equation 13.
Old equation 13, dude. So 20, 23, and 24 are all going back up to the top there to meet your boy Sagnac. Peace be upon him. When the clock moves eastward, we understand that the velocity of the clock is added to the velocity to the Earth velocity, so that the term lambda becomes larger. For the moving mass mu, the clock in motion, and then for the masses, clock alpha and beta, which don't possess any extra velocity because they're stationary. Consequently, the clock moving eastward runs at a slower rate. Consequently, the Einstein synchronization method is not compatible with the time given by GPS, and the Sagnac effect must be added. Finally, we conclude that the difference of the clock synchronization given by equation 13 is an experimental fact that has been observed when setting up the Okay. All right. We must conclude that the velocity of light is equal to c with respect to the non-rotating frame.
Experimentally affect whether or not you include lament symmetry.
Sorry, say that
You
again.
good?
Yeah, I was just stretching and yawning at the same time.
I was just saying experimentally affect regardless of whether you want to include Lorentz
Oh.
symmetry or not.
Yeah. If you want to get Lorentz involved or not, bro, this clock does not work with Einstein.
It's gonna our lab frame result much you can go into fairy tale land in your head as much as you want, but the lab frame result is consistent.
All right, let's see. GPS and the constant velocity of light. Synchronizing the clocks with GPS. God damn, there's a couple more pages left. Other experiments can be realized to test the clock difference between clock. Other experiments can be realized to test the difference of synchronization time between clocks. Experiment of the north-south displacements of the clocks has also been verified experimentally. Oh, no way. I thought this had. Oh, okay. I was under the impression that there was no relationship here.
But experience north-south displacements of clocks? Oh.
Yeah, I was under the impression that going perpendicular to the preferred direction doesn't Well, I guess it would experience like normal desynchronization or whatever, and it would still have to be moving through the ether, so it's gonna generate its own proportional velocity.
Yeah,
Okay, yeah, okay, okay,
I think that makes sense.
yeah,
Okay, this is interesting. Wait till you read down more.
okay. Instead of directly exchanging the radio signals or the moving clock between New York and San Francisco, as in the illustration 3, let us assume that the radio signal was sent from New York to from the station to the North Pole of the Earth before being reflected or re-emitted to San Francisco. So they're gonna make a triangle. Okay, yeah,
Yeah.
yeah. Okay, okay. So the North Pole being reflected before that. Okay, this can be done using a satellite located at the North Pole. Yep. And in this case, in agreement with GPS, we observe. What's that?
Yep, that's it right there.
Yeah. In agreement with GPS, we can observe that the simultaneous exchange of the radio synchronization between A and B does not show the difference of 14 nanoseconds since the light travels across the meridians.
Never,
What?
since light never travels across meridians. So they're saying
That it's not
he's saying,
changing, right?
yeah, he's saying that if you go triangularly from A to B, but hitting somewhere in the North Pole first, that you will not see that 14-second nano delay.
Oh, well, doesn't that make sense though? Because it would be canceling out because you're going perpendicular to it and then back around. Wouldn't that make sense that it would cancel it though?
I don't know. Honestly. So it's on the same meridian. It's not traveling across meridian.
Because if it's just the signal, it wouldn't. I wouldn't even expect it to unless it was something that was in motion. Unless it was, if it like just the signal by itself, I wouldn't expect a bias going perpendicular to the preferred direction. But what I would expect is if you were in a truck or something, traveling in that direction, the velocity of that, uh, motion
Moving.
would create a variance. But what they're saying here is that there isn't any. So I think I would agree with that.
Scroll down.
Okay.
Let me read it again.
Oops, I think was it this one? Yeah.
Yeah. See, then light never has to move directly against the Earth's velocity of rotation. So it says, yeah.
Yeah. So you would just equate that in the same way with an ether wind. So, oh, my bad. Yeah, what's up, President Brandon?
I was just gonna say, check your Telegram.
Oh, check my TG. What we got going on here? Oh, nice, bro. Nice. Hell yeah. Play it out here when we wrap up this. We're about to finish up this paper, and then I'll play it out.
Oh, you did it, dude. Nice. You've been cranking them out.
Hell yeah.
Sorry I couldn't make it to this. I thought this was tomorrow.
No,
not
no,
today.
this is just us chilling. You're good.
Okay, cool. We
still got tomorrow.
Be at the round table tomorrow, I guess.
Heck yeah.
Hell yeah.
Yeah.
All right.
Sorry for interrupting.
No, you're straight. You're straight. Let's see here. So yeah, going against or not going against it or whatever. Okay. So equivalent to ether mechanic. The projection of light, the defined equation 23 is 0 because light travels along the meridians of the North Pole. Of course, there is a higher order correction related to the transverse velocity of light with C, which can be considered elsewhere, but this is clearly not observably experimentally.
So there is maybe something going on there that they're just not noting.
So of course, there is a higher order correction related to the transverse velocity of light with V that
Wait
can
a
be
second.
considered elsewhere.
Wait till you read more.
Shit.
However, it is has been demonstrated that the flatness of the Earth.
Let's see. Okay, a similar result is obtained. What's that?
What if he's a low-key flat earther, this dude?
That'd be awesome. I doubt it.
Yeah, me too.
So let's see. A similar result is obtained when we carry an atomic clock mu at a constant geodesic altitude in the north-south direction from New York to the North Pole. In that case, the clock mu might increase its rate because of the increased tangential velocity of the Earth rotation at higher altitudes. However, this has been demonstrated that due to the flatness of the Earth, that there is a. However, it
It's
is
a
demonstrated that the flatness of Earth is such that the gravitational potential at the pole compensates exactly for the loss in rotational velocity, since no meridians are. Oh my god! So they're literally, because you know how they say that at the poles it's slightly flatter because of the rotation and gravity and all that bullshit.
Yeah.
So they're saying that gravitational equal potential difference there, or what would be like an equal potential gradient, is obviously thrown off. But that difference causes a. It's basically compensating for the rotation of Earth. Like it's uh, canceling
Oh
it
my
out,
goodness.
That's so they're that's how they're justifying that. Increases its
Just
rate
happened.
due to the
Wow.
tangential velocity at altitude. However, it has been demonstrated that the flatness of Earth and such a gravitational potential causes exactly for the loss of the rotational value. Since no meridians are crossed, the GPS correctly calculates a zero correction to the clock at its arrival at the North Pole. Yeah, so it's saying that that due to the flatness of Earth, because it's traveling perpendicular to the ether wind, there's no correction. But to explain this on the glob, they're like, it's traveling, the gravitational gradient's different because the poles are flatter, so it doesn't fall off quite at 2 pi 4 r squared or whatever. If the gravitational potential falls off at like a slightly different rate. Like, dude, that's like the freedom that they could get away with, just by invoking like flatness in a certain spot, man. Like they're like, oh, it's throwing off the gravitational potential, Toby.
Yo, dude, do you question your technology?
Don't look
You're on
into
the computer
this.
right now. You're using GPS.
Do
Your
you
iPhone proves a globe.
do you realize that the electrons and transistors in your computer right now are proof that we live on a globe? You stupid flurf. Oh my god.
A similar result is obtained when we can turn an atomic clock mu at constant geodesic altitude. Okay, so yeah, this is. However, has been demonstrated the flatness of the Earth is such that the gravitational potential at the pole. Just fucking nonsense, dude.
Yeah. Yo, Beast, you want to take over and finish out reading this out loud for everyone?
Sure.
I'm tired. Thank you.
Me too, dude.
I can read if you don't want to.
Since no meridians are crossed, the GPS correctly calculates a zero correction on clock mu at its arrival at the North Pole. For the same reason, a null correction is also calculated on clock mu at the GPS when it is moved from the North Pole to San Francisco. Either using simultaneous light transmission or carrying a clock mu, it is remarkable that both methods of synchronization of clocks between New York and San Francisco across the North Pole give an identical zero correction. However, when the radio signal or the moving clock crosses the meridians, the correction of 14 nanoseconds, as calculated by equation 13, appears in both methods. That's interesting, actually.
Okay. So, let's see. So,
It is pretty interesting.
however crosses the meridians, the correction, is it 14 milliseconds per meridian, or is it just
However, when the radio signal or the moving clock crosses the meridians, the correction of 14 nanoseconds, as calculated by equation 13, appears in both methods.
Because
oh,
those are the only times you're going with
yeah,
or against either
it's
one.
yeah, okay, it's catching the ether wind, right? Dude. Suddenly feeling very etheric around here. All right, very cool.
What else is left?
Just this part right here, and then the conclusion. So one more page, essentially.
Okay. Measurement of the velocity of light as c plus v. Knowing that the Sagnac effect, the GPS, all the related experiments described above, and also using Newton physics led to identical results, we can rely on the GPS data. Consequently, the GPS is a reliable tool to measure directly the one-way velocity of light. Let us start our experiment with an atomic clock at the North Pole of the Earth. At this location, there's evidently no problem about the Earth rotation, which is absent from the North Pole. Let us initiate an independent synchronization with the two clocks A and B, located respectively in New York and in San Francisco. Since both methods, transmission of simultaneous radio signals or carrying an atomic clock, lead to the same result, we can use the synchronization method of our preference. From the North Pole and moving along the meridians, the projection of the path on the Earth equator, A sub E, is 0. Consequently, in that case, synchronizations of the clocks in New York and San Francisco with the one at the North Pole do not need any correction. A sub E equals 0 in equation 22. Two clocks in San Francisco and in New York are in perfect synchronization. Using this synchronization, let us measure the velocity of light between New York to San Francisco and also between San Francisco and New York. Let the observer in New York send a radio signal across the meridians to San Francisco at the same time as another radio signal travels in the opposite direction. This simultaneous exchange of radio signals can be done using the refraction of the ionosphere or via satellite at a low altitude above the same meridian. Since the two clocks have been previously accurately synchronized in the paragraph above, the absolute time of emission and reception can be measured directly on each local clocks, A and B. If the path length of the radio signal is not much longer than the shortest path passing across the meridians, the average time interval measured simultaneously in both directions is about 1500 or 15,000 microseconds. However, an accurate measurement of the time interval given by the GPS shows that the light takes an extra 0.014 microsecond for light to travel eastward from San Francisco to New York. Also, light arrives at the western station from New York to San Francisco 0.014 microsecond before the average 15,000 microseconds interval needed to travel a distance of about 4,500 kilometers. Since there's a difference of 0.014 microsecond in each direction, this shows that light moves at a different velocity eastward than westward. We calculate that the velocity of the rotation of the Earth at the latitude of those cities is about 1/millionth of the velocity of light. From the above data, the time interval for light from New York toward the approaching San Francisco is about one.
Did they just call this relative simultaneity?
What's that?
Did they just call this relative simultaneity, basically? Is that what they call this?
No.
Okay. So this is just Lorentz transformed at different rates both ways.
No, this is just not acknowledged.
Well, yeah,
yeah. This is just this is nobody. This is why this guy lost his everything, and died of bone marrow cancer.
Well, Matt would basically tell us that Lorentz transformed both ways.
Well, you couldn't do that because the Earth's only rotating in one direction. So if you were going to believe in opposite direction rotation contraction, like that wouldn't it wouldn't work for him if you tried to.
It's insane.
Because he's actually going to point that out here in a second. So
right, sorry, you can continue.
Yeah, you're good. You're good.
Also, the time interval for light to move from San Francisco to New York, which moves away, is about 1/millionth longer. Clearly, the velocity of light with respect to an observer resting on the Earth's surface is c plus v between New York and SF, and c minus v between SF and New York. Therefore, the velocity of light is c only with respect to the non-rotating frame. Absolute reference frame of reference. One must conclude that the GPS and all the related experiments giving a striking proof that the velocity of light is not constant with respect to an observer, contrary to Einstein's hypothesis or hypotheses. The measured velocity of light is c minus v in one direction and c plus v in the other. The velocity of light is equal to c with respect to an absolute frame in space. This is now an experimental fact. Finally, we have seen how it is apparently constant in all frames using proper values due to the synchronization used in physics. We have considered here the velocity of light with respect to a group of stars around the sun.
However, there is nothing that indicates that the star cluster is at an absolute rest. It probably moves around our galaxy, which in turn moves around the local clusters of galaxies. From what we have analyzed, we see that the star cluster mentioned above is just another moving frame in which once more we have an apparent velocity of light equal to c in all directions. Because we do not know yet how to get an absolute synchronization of clocks. There does not seem to exist a simple way to use light in the above experiments to determine the absolute velocity with respect to the fundamental frame of the universe. We have mentioned in a previous paper, Marmay, 1995, that there seems to be an absolute frame of reference related to the 3K radiation dipole in space. However, other than using the 3K radiation, light seems to be inadequate to verify our absolute velocity with respect to an absolute frame. There is another solution to locate that absolute frame, but this is beyond the scope of this paper. Most physicists believe that the velocity of light is constant with respect to all frames. As explained above, this is wrong. Let's go back to the question. The velocity of light is c with respect to what? The principle of mass energy conservation implies that light moves at a constant velocity with respect to an absolute frame. Furthermore, in all other frames, the velocity of light is measured to be constant equal to c with respect to that moving frame. However, this is an illusion due to Einstein's discordant clock synchronization. Some scientists suggest the existence of an ether to carry light. A rudimentary ether hypothesis leads to an observation of the velocity of light that can be measured directly as c plus or minus v with respect to the observer. It is not that simple. One extremely important point is that there is no observational justification, Marmet 1999, to assume that an ether can possess its own energy that can be borrowed when needed. On the contrary, all the physical phenomena are explained naturally without having to borrow any energy nor momentum from an assumed medium. For the moment, the sole property of that assumed ether is to establish an absolute origin of the velocity frame of light and physical matter, because this frame of reference is absolutely needed to comply with the principle of energy and momentum conservation. One must conclude that there exists no space-time distortion of any kind. It is no longer necessary to fascinate people with the magic of relativity, unless we accept that the absurd solution that the distance between New York and San Francisco is smaller than the distance between San Francisco and New York. We have to accept that the velocity of light is different in each direction. As mentioned above, this difference is even programmed in the GPS computer in order to get correct global positioning. This proves that the experimental velocity of light with respect to a moving observer is c plus or minus v.
Dude, he threw the gloves off in the end there.
Sure did.
Yeah, it's just like, you know what? I don't like ether. What did it talk about right there?
Which one?
It is not that simple. One extremely important point is that there is no observational justification to assume that an ether can possess its own energy that can be borrowed when needed. Isn't that essentially saying it's like dark matter?
No, I think he's saying you can't substantiate its existence or lack of existence.
Yeah, he's utilizing the framework while simultaneously saying that the mechanism that the ether provides isn't providing the variance in C. So he's using it for the frame of reference to have an absolute value, but he denies the mechanism of the proportionality where it varies proportional to the observer or velocity of the observer. So that he's just trying to remove the mechanism of the ether so that he can keep the contraction in time interval difference to his energy equivalence situation.
Yeah, he's like without saying. Basically, it's also just like without asserting too much at once. Really.
Yeah. So
kind of what
I've been listening to almost this entire thing, and it sounds like a whole bunch of begging the question, like constantly.
You mean begging the Einstein? Begging the frame? It's begging the frame,
yeah,
bro.
And like just appeal to consensus, and I mean, there's so many logical fallacies in this. It's ridiculous.
Yeah. Well. Yeah. All right. Well, I appreciate you reading that, Toby and Beasticles. finishing us off there.
Dude.
It was a long one, but it's oh wait, here's some gravy. What's this giant arrow do? What's this mean? So the discordant synchronization given in equation 13 has measured in the world system of clock synchronization with GPS positioning. It is then observed experimentally that the Einstein method of synchronization using the half-time interval taken by a reflected light beam is inadequate to determine the correct time. A correction, which is the Sagnac effect, has to be added. Oh, no way. So it's inadequate to just assume that the speed of light is the same in both directions uniformly in perpetuity, and that there's actually a fucking variance proportional to the velocity of the thing that is, or, to the observer. Yeah. Awesome. And then what was that? What was that? Oh, this is the 1/2 synchronization to account for that, for the Einsteinian synchronization. And then we're going to go look at equation 13 and say goodnight to Sagnac. Let's see, equation 13. Where's 13 at? Oh, here we go.
Here it is.
13. Shout out to your boy Sagnac. Peace. All right. Oh, man. What an awesome paper. What an adventure. What an adventure.
What an adventure.
Let's see. Was there anything else? We covered a
better than
lot.
Rust, dude. Way better than Rust.
We covered a lot.
Yeah.
Am I incorrect in thinking that Cavendish was before Newton, and so this is off topic. I'm researching, but it was before Newton, and so it wasn't actually to prove gravity. It says here it was to prove
It was to weigh the
density of
Earth.
Earth.
Yep.
But then doesn't Einsteinian special relativity invalidate the Newtonian gravity at like the mass attracts mass at the same time?
No, it's a complementary extension through the mathematics using a principle called covariance. So, although it technically, supersedes it, and you'll often see different, even mainstream sources look like it superseded Newton, and then you'll see no, they're interchangeable, and like you'll like all this dog shit. Like mathematically, they're interchangeable. The description of me dropping an object on my desk and it falling to the center of the earth is the same as me dropping the object and it falling along a curvature to the center of the earth, even though the curvature is imperceptible from our perspective. What's up? Like obviously it's retarded, but mathematically through covariance, it's not that it supersedes. It's that they look at it as an extension or a further understanding of the Newtonian framework. Is what they'll actually tell you is that Einstein's field equations reduce back to Newton's equations, so they use that covariant relationship to extend a what would you call it? To extend like an olive branch to the validity of space-time contraction, because everybody already agrees of Newtonian physics and Newtonian mass attracting mass to explain everything in the sky. So they used that as the jumping off point. So it had to be backwards compatible with Newton. So that's the answer to that.
Right, because when I had the whole graph thing I was talking about with my brother, he pointed directly at Cavendish's experiment, and also, let's see.
So,
the fact that people have been to space and then pulled back down by gravity or escaped the Earth's gravitational pull at something like 40,000 miles an hour and 6 miles.
Yeah.
To me, that's pretty convincing.
Yeah.
But that's kind of like an appeal to authority that he's building his thing off of.
Yeah.
All the way.
Yeah.
He hasn't observed a phenomenon, as far as I understand, either with the Cavendish experiment. There's no natural phenomenon being observed.
Yeah.
Like, there's an effect being observed, but there's no actual molecule, physical thing for it to be an actual experiment, right? Or I don't know. I'm trying to figure this out so I don't fucking make my life harder with my answer.
All good, dude. I gotta wake up in 5 a.m.
Oh wow, you ought to go. I gotta get up at not quite that early, but I do go to work tomorrow.
It's all good. I'm in some bullshit ass fucking module training for my new job, so it's like fucking chill and Zoom meetings. So I'm like back and forth and